Alrighty, looks like we're live. All right. Okay. So, to everyone who's watching in the future, welcome back. Or thank you for watching the stream. The replay, anyway. All right. So, today what we're going to be doing is port. Okay. So, we've been building that balancing robot over the last couple of streams. Today we're switching topics. We're going to be looking at porting an Arduino sketch from, porting an Arduino sketch over to an RTOS framework called ChibiOS. And so there are a couple of RTOS frameworks for the AVR, that support the AVR. Probably the big one that everybody knows of is FreeRTOS, which we were using on the PyPico when we were doing the balancing robot. But one of the others that's out there is called ChibiOS. And ChibiOS, I believe, started mostly in the STM32 world, but it is an extremely minimal, performance-oriented RTOS, and it does have an AVR port. I don't know how popular the AVR port is, but it does support it. And as far as real-world projects that use ChibiOS, there's probably the big one that you probably heard of is ArduPilot. It uses ChibiOS, and then PX4, which is the other big one, uses NutX, but NutX doesn't run on the AVR. It's a bit too performance intensive. NutX being they will sacrifice performance in order to maintain a certain development environment, to maintain their POSIX compatibility. But either way, so why the port to ChibiOS though? So one big one is that I just wanted to check out ChibiOS, big one is I just wanted to check out ChibiOS. The other is that there are a number of I2C sensors in the robot, and if you've ever worked with the Arduino wire class, their wire device in the Arduino framework, you'll know that it's blocking. So whenever you want to make an I2C request, you have to start the request and then wait for the response. And I2C is not fast. It's not the slowest of the serial protocols, the typical serial protocols, but it is not very fast. You still have, even at the maximum, even at the relatively modest settings, you're still talking about several hundred and 100 or so instructions, passing per. Actually, sorry, it's even worse. Several, potentially 1,000 instructions passing before you get a byte of data across the bus. So if you're just sitting there waiting for a response over I2C, you're spending 99% of your CPU cycles just stalling, waiting for a response. So there are a couple. There's nothing preventing us from creating our own, asynchronous, I2C implementation inside of the AVR framework. But the default one is blocking, and in ChibiOS, it is not blocking. They have a fully asynchronous, the API is blocking, but because you have threads, you can have other threads doing work whilst your I2C task is blocked. So kind of the idea here today is that we have this robot. Let me grab the desk camera here. Wake up my phone because I'm running Droid Cam. Oh, nope, that didn't work. All right, let me turn on the desk camera. Alrighty. So we have got this robot. Its name's Kybernetes 2. I've entered it in several Robomagellan events over the last couple of years, and it's done pretty well. I've taken gold in every single competition I've entered. And what is Robomagellan? So essentially, what this robot is designed to do is it navigates in an outdoor park-like environment. It has GPS. It has a compass. It has odometry to measure how far it's driven and how fast it's driving. It has a stereoscopic depth camera in the front as well as a color camera. So there are 3 cameras up in the cluster there. It has some AI capability for doing air quotes AI. Don't get me started. It runs that camera up front is an OAK-D Pro wide angle, OAK-D Pro W, and it has a small amount of bandwidth available for NPU, so you can run small neural network object classifiers like YOLO on it. And so I have trained it. Well, I should say I found I have tried to train it, but I have found better models that have been more thoroughly trained on the internet to recognize traffic cones, which are the target object for this robot. Essentially, the competition is you have GPS coordinates of these traffic cones in a park, and you have to autonomously get from the starting position to the ending position, both designated by traffic cones. And there are a number of bonus cones along the way that give you essentially a time multiplier if you can hit them. And so, essentially, what the architecture of this robot, there is an Arduino in the lower part of the chassis, in that little green box, that manages essentially controlling the speed controller, controlling the steering servos. It reads the odometer, or the shaft encoder to provide odometry and velocity control. It is also plugged in, it also provides the I2C bus for the system, which at present is connected to another AVR, which talks to the RC radio, and talks to the current, a battery current sensor that measures the to monitor the logic power supply, and it is also plugged into this new IMU that I've installed called the USFS Max. Although this IMU is not working, and actually this IMU today is the whole motivation of doing this work. So currently the sketch does do blocking I2C operations for reading the radio and such, but those don't generate a ton of data, but this IMU, on the other hand, does generate a substantial amount of data, and my early experiments with it, I found that almost all of the CPU cycles of the Arduino are responding to this thing needing data to be moved to and from, moved off of it. So essentially, we're trying to free up cycles on the Arduino so that we can actually capture the data from this IMU and pass it up to the rest of the robot. And so the rest of the robot, there is this black box on the back is actually a GPS receiver. The actual GPS is under that coil wrap. It's a U-Blox F9P RTK capable GPS. So, which means that you can feed it GPS correction data from a stationary receiver. And with that whole thing, with RTK running, you get sub-centimeter precision, but the competition rules typically disallow the usage of RTK. But this unit is capable of around plus or minus 2 foot, 1.5 to 2 foot, so half meter accuracy all by itself, because it's able to lock onto multiple GPS constellations simultaneously, and with a decent view of the sky, the location estimates are extremely precise, even without correction data. And obviously we talked about the camera, and then the whole primary brain of the robot is a Raspberry Pi 4. And then there's another IMU installed in the front, which is the one that is currently actually used, but that one connects directly to the Raspberry Pi. And the rest, there's also these two bumpers on the bump sensors on the front that measure whether we've contacted the cone. And so, back to the desktop. So, let's see, where am I going? Oh, my webcam froze. Hold on. Webcam is frozen. Okay, brilliant. Can we see the mouse? We can see my mouse, but you can't see me. Okay. Let's hit the settings on that. Logitech. Camera. Nope. Brio. Oh god, sorry. Nope. It's really unhappy with me. Let me power cycle the camera here. Although, I guess you don't have to see me. It's not required. It's just a lot of people do put their web cameras up. Alright, reconnect the camera. Trying to get the Brio. Oh, there we go. Alright. We're back. Oh, wow. It has decided to Resolution 1080p. Okay, there we go. All right, webcam's back. Sorry about that. All right. Okay, so ChibiOS. We talked about the robot. Let me power this thing up real quick. Which, back to the desk cam. All right, so we're going to take our two lipos. Come over to the robot. We are going to get one lipo, which drives all of the motors. We'll plug that in, and then we get another lipo, which powers all of the logic and all of the sensors and such. And as it's a Raspberry Pi running Linux, it will take a minute or so to boot up. All right. So, desktop. Okay. Back over here. Okay. Okay, coming up. All right. So, start with fetching ChibiOS, or actually, let's start with fetching the code for the existing motion controller. So Kybernetes motion controller. All of this is uploaded to GitHub, by the way, links in the description. So essentially, this is the core sketch of the robot. I'm not super proud of the code quality in here. It's honestly not my greatest creation, but what we can do, but either way, so the whole point of this little series here, I guess, will be we're going to be refactoring this Arduino code into a ChibiOS project, and making improvements along the way using the features of ChibiOS to make this code cleaner and better. Particularly, actually, I'm not super unhappy with it. Mostly what I'm unhappy with is the state management. But the fact of the matter is, the code works. As ugly as it might be, the robot runs, and it does what it's supposed to do. But we're just trying to make it better because it suffers from hobby project syndrome, as it were. All right, so let's get in here. All right, so I do already have the ChibiOS, it's not ChibiOS, I'm sorry. I do already have this Kybernetes motion controller code downloaded. So I'm on the development branch, but I will fork this to, actually, we can just leave this on the dev branch, right? So I will start by adding a git submodule. We'll start. I'm talking over myself here. We're going to start by adding a git submodule for ChibiOS. So we're going to do git submodule add. We're going to use the GitHub mirror for ChibiOS. So that's github.com/ChibiOS/ChibiOS. We're going to call that ChibiOS. Alrighty. Alright, so we have a submodule for ChibiOS. And now we're going to make sure that we actually check out not the master, but essentially a officially released version. But I think, okay, hold on. What is the latest tag that's in here? We're talking, you know what? Let's see, HTTPS, GitHub, Chibi. And the latest official version is version 21.11.3. So we're going to check out ver 21.11.3. 21.11.3. All right. Perfect. So now we're on version 21.11.3, which is an officially, released version. So let's just add our Git submodule here. Add ChibiOS submodule. Cool. Go to ChibiOS. And probably one of the things we should do first here is just check out some of the ChibiOS samples, especially just to see where we're starting with. Because the ChibiOS is going to feel... writing code for ChibiOS is going to feel more like writing a standard AVR GCC project rather than an Arduino sketch. In Arduino sketch, you're used to having your setup function, your loop function. Setup's called once, loop's called in a loop forever. ChibiOS, you get main. Main is still main. It feels like normal C development. I mean, Arduino is basically the thin wrapper over C, but C++. I'm sorry. ChibiOS is C, not C++. Either way, so let's go to the demos folder. We're gonna go to AVR. The robot may be over there, but just so we don't mess with too many things, I have a little Arduino Uno here. It's the same variant as the one that's in the robot. I'm gonna just plug that in over here. Well, not quite yet, but leave that on the desk. We're gonna check out. There are two versions of the kernel for ChibiOS. There is ChibiOS nil, and there's ChibiOS RT. Nil is essentially just a round robin scheduler. No thread priorities. That just whatever's runnable is runnable. RT is is a lot more featured. It has virtual timers, so you can say I want to execute this task. I want to execute this task in the interrupt context, or the thread context, the timer context, on this interval. Whereas nil is it just provides the threads. It provides a couple of synchronization primitives, and the ability to sleep, and that's about it. Nil, it's so small it might as well not be there, I think was the kind of their slogan. But all right, so let's check out nil Arduino Uno. And what happens if we type make? Well, it built, but AVR size is complaining. Okay. I guess their make file is not... What version of AVR size do I have? Version? I guess 2.44. Well, I mean, I'm running Gen 2, so I have pretty recent... my AVR compilers are pretty up to date. Let's see. So AVR size... Oh, interesting. I guess that's not in here. Oh, target size SZ. CU format AVR. Select output style. Well, we'll just delete the out. Well, clearly this format command is not what it used to be. So we'll just delete that and see what happens. No, that didn't work. Output style. Might not even need some of this stuff anymore. We'll see what happens. Look at that. Now it works. Okay. Size. There's some warnings because I have a more recent compiler than it probably was built with. Either way. Okay. So we've got this sample project, and let's actually look at what this looks like. So let's do this. All right, so the sample, we are blinking, we're toggling an LED. So this is how things are defined in nil here. We got this function basically says it defines the stack for the thread. This defines the thread. It toggles the LED pin, sleeps 500 milliseconds, so the LED is going to flip state, so it blinks once per second. Function 2 starts the serial port and then prints out a message every 2 seconds. And then this defines a thread table, 1 entry per thread, and then the entries must match nil config num threads. Interesting. Nil config num threads. Maybe that's a define in here somewhere. No. Either way, let's continue. Oh. System initialization, all they do is init the HAL, that sysinit, and then there's a loop. This is now the idle loop. You must never try to sleep. Oh, okay. Well, all right. So I saw that there is AVR dude in here, so I wonder what programming it's going to involve. But, you know, like all Arduinos, mostly comes up as ACM0. So we'll just save that. How do I wonder if there's a make flash. Is that what programs? Make install? Oh, it's mad at me now. What did I do to the make file? Oh no. Did it always do that? Oh, it always did that. Okay. Make program? Ah, alright, cool. Perfect. Okay, cool. So we're going to plug in an Arduino. We got our Arduino Uno. I say make program. Hey, now it is programming, potentially. C wiring. Timeout. Maybe that's not right. Maybe AVR dude programmer. Programmer ID is Arduino, maybe, I think. Make program. Ah, there we go. Cool. Writing code to the Arduino. Now, if we do minicom, actually, what baud rate did it set the serial port to? Did it say in the code here? It just said serial start. So maybe there's a CFG folder. Let's see what this says. HAL conf. What is this? SDC. There's a lot of stuff. Default SIO bit rate 38400. How about serial driver related setting? 38400, it looks like serial. It looks like 38400. So what happens if we do minicom ECM? Hey, hello world. There we go. Cool. We are running a ChibiOS project, and as we can see on the Arduino itself, maybe hopefully you can see that the LED is in fact blinking, or I should say this one over here, the L one. So yes, the transmit light will blink whenever it sends a message, but hopefully you can see the once a second blink. All right, so it runs. How does let's see if okay, so I'm still not entirely certain if I want to select ChibiOS RT or ChibiOS nil. But we'll start with nil, and then, or actually before we start with nil, build config. I think chconf is ChibiOS config, and so nil. How do I must equal nil, such as this code, must equal nil config num threads. The number of entries must equal. So how about we search for nil config num threads? So in main.c it defines, it says that, but then in no files in here does it actually define nil config num threads. Maybe it really is maximum number of threads. This number is not inclusive of the idle thread. Set this, or you'll be wasting RAM and cycles. Chconfig. This value also defines the maximum available priorities. All right. Well, maybe some timer allowed is 32 bits. Frequency, system tick frequency. Option defines the maximum amount of time allowed for timeouts. Well, so, okay. Well, so if the system tick resolution is 16 bits, and the tick frequency is 15, that means the system timer is going to roll over every 4 seconds. Okay. So that means that you can't sleep longer than 4 seconds. Okay. That's honestly fine. I think the longest sleep we have is the 20 or 50 milliseconds, so that's okay. Time delta... Okay, well, anyway, we can always change whether we're using RT or nil in the future. So let's just start here. So let's copy this make file up to our motion controller demo. So slash dot dot slash dot dot slash dot dot slash. Yeah, all right. All right, so if we edit this make file, well, author Theodore Ateba. Well, I'm not that. I'm. Oh, I don't know if you're supposed to update this to your own name or not. Oh well. And I am git at. All right, cool. Make file. Our project is going to be called Kybernetes Motion Controller. And our ChibiOS dir is actually /ChibiOS. Alright, main. We're going to say we have Kybernetes Motion Controller.c. What other files do I have in here? We got CRC, we got Kybernetes Motion Controller. Oh, that'll actually be .cpp, sorry. So, and we're going to need to do usfsmax.cpp. Okay, cool. Make file crc8.cpp. This could be .cpp. usfs. I think that was everything, right? That's all the .cpps. Okay, yeah. And then we're going to move Kybernetes Motion Controller from Eno to CPP. Perfect. So we type make. Recipe commences before first target. That's not good. What? Oh, we're going to... Okay, so we need to copy halconf, chconf, chconf. Okay, sorry. So we got a couple more things to copy from the sample. So ChibiOS demos... ABR, nil, Arduino, Uno, config to dot. Alright, cool. Vim config chconf. So what we're going to do is actually change. We want to run at 15 or 115.2 kbaud. So we're going to change. That wasn't in mcu.conf. That was in... That was in... halconf. Hal use pal. Hal use... Alright. Use serial. Default bitrate, and it changes to 115200. Serial buffer size. Default, we're going to change this to 64 bytes for the buffers. SIO, this will go to, oops. And just so everybody's aware, I have never used ChibiOS, and I've never written a ChibiOS project in my life. I did check it out. I did check out some of the examples like 9 months ago, but I've not actually written a project around this before. So this is me learning too. I'm just reading through this sample here. All I've done is do some reading. All right. Well, maybe that's all we need to change for now. Cool. Did it change anything else in here? Oh, geez. Do Do not recurse is something I really should be able to tell it. Yeah, CFG didn't change. Where's serial in the make file, maybe? Does it do anything? No. Okay, cool. Recipe commences before first target. Well, it's still upset at me for that. So what did I miss? Oh, oops. Well then, I need to do that. I need to do... These are all CPP files, so that probably was one thing it was upset about. So... RGC, size, project elf, size report. Did I do anything particularly wrong? Hold on, CRC 8. Nope. What's on line 115? Oh, I'm stupid. Well, I'm not stupid, but sorry. I need to put those back tick marks on all of this. Okay, cool. There we go. Now we're building stuff. But we hit our first error because none of this shit exists on so a lot of this logic doesn't exist in ChibiOS by default. We need, quadrature encoder implementation. We need a bunch of other stuff. So there's a lot of stuff here that's not going to just work. That we're going to have to write and or find on the internet somewhere. So, yeah. Wow, I'm blanking again. Jesus. Okay, yeah. So, one of the things we have now lost is all of the default Arduino logic that is all the default Arduino utilities and helpers that have been written over the years. So, we're going to bring this up in Visual Studio Code. And we're also going to bring up our web page here. We're going to just bring this over. I'll zoom in a little bit so y'all can see better. Okay, so Kybernetes, it's 700 and some odd lines of horridness. Okay, we'll save that. Okay, actually, and so before we get too much into this, tabbing out of this just made me realize. Okay, so I do have some videos of the robot running around. So this is what this competition actually looks like, right? So the robot had started on the other side of the park, and it's traveling over looking for these cones. And so you can see my Instacam hanging there off the back. But it runs around and it looks for these orange traffic cones. So it's got close to one. It saw it, so it stopped. Now I have it programmed where it'll only stop if it sees one within like either 5 or 7 meters of where it's trying to drive to. And so it bumped that, it runs off the other way. It goes for this other cone, which is the target, the final destination target cone in this case. It hits the brakes way too hard, but runs in and tries to get that. And it'll stop once it finally hits it. Alrighty. And then, from that Instacam's perspective, it's running in the back. It's kind of got the flyby cam, right? Alrighty. Just to show what this robot actually does. And so, or I guess, bring back my terminal here. It should be booted up by now. So sh Kybernetes.local. Actually, we can use Mosh. Cool. Update. Running Raspbian something or another. All right. Cool. We got the robot is up. All 4 of our cores on our Pi 4 gig. All right, sweet. All right, so where to even begin? As we've got, if we type make, You know, obviously, first thing that fails is there is no encoder.h, so let's comment that out. There's going to be all those things we have to replace. So Kybernetes dot a why is it complaining about this? Go to definition, program space, go to oh, okay, right. Cause this is Visual Studio Code and there's a lot of things that it doesn't know. We'll comment that out, comment that out, comment that out, because none of those headers are going to exist in our new and brave world here. We're going to edit the squigglies, edit the include path. Sysroot, configuration to edit, Linux, oh dear. Where does, oh, right, that's why. Where does Gentoo put our, I think it's USR AVR include, yeah, okay. And then, actually, let's find all the .h files in USR AVR. Find .-name. Let's just AVR/include. Yeah. Okay. Cool. Search folder. Include path. Compiler arguments. So yeah, sysroot. Okay. One argument per line. Oh, I didn't like that. Let's see what happens. Oh, ew, oops. Ooh, I made it mad. I made it mad. Let's take additional space to limited argument should be entered as. Oh, I see what I did. Okay. I've really made it angry. Alright. By making sure that the compiler can't compile, I now get no errors. Include path. We'll just be dumb. USR AVR include. Perfect. Now we don't have to deal with this. Okay. Go to definition. Right? Yeah, there we go. Perfect. Now we can get to program space. Alrighty. CRC lookup table, progmem, cool, cool, cool. This is all working. Nice, alrighty. Well, so now that we've removed all of the includes that don't work, we're going to get a ton of errors on all this logic that we previously used that doesn't exist anymore. Yeah, lots of errors that we're going to have to fix. Oh, this isn't even invalid conversion, F permissive. Hoo-hoo. This is all stuff that you can get away with in Arduino that you can't get away with in standards. So we're gonna maybe we just disable this warning. Invalid conversion from. Oh, why am I casting? Calculate CRC8. Sorry. Oh wow. Why did I know? Oh. This is something Arduino didn't catch that I should have always done. Data, yeah, it's not like I'm modifying data, so that should be that should have always been const. What? Why did Arduino let me get away with casting constants to non-constants? That's terrifying. Why did it ever let me do that? Okay. Either way, serial's not declared in this scope, right? Obviously, digital read. All of this stuff, memset's probably in this other thing. Wire doesn't exist. Function that doesn't return void. Oh, because this was a bad struct definition. No, wait. Operator equals. Yeah, and then I never... Huh. There's all this stuff that Arduino would let me get away with, that the standard Arduino compiler wouldn't, standard AVR compiler wouldn't let me get away with. That's funny, and scary at the same time. Kill switch state, const state, handy short. Wait, why is this bad? A reference to kill switch state, non-const qualified, cannot be initialized. The value of kill switch status packet. Oh. Return. Is that what I wanted to do? Return state. Huh. Oh, wait. No, that should have been fine, right? Taking the address of a bit field is not allowed. Okay, fair. We'll just leave that at what it was initially. Non-const return, which is... Okay, wow. That's something that should have been caught in the past, but was not because Arduino. But, okay. Fun. Attribute packed. Ignored. Couple of fun ones here. UFS max types. Packed is ignored. Just packed. Is that not ignored? Oh, that's fine. Wonder if that's even valid in here. Expected initializer before pack. Okay, I gotta look up what that actually is here. Anywho, we'll do that. We'll figure that out in the future. So memset needs to come from string.h or cstring. Because we get cstring in memset wire dot. Where's memset? Where did that memset come from anyway? Memset, not in there. Wait, hold on. That's not the thing that was throwing an error. I remove a goldfish. Okay. We need to memset should be derived from in function. Oh, that's PID frame, not that one. All right, cool. Memset reset. This size of this 0. Perfect. Okay, cool. Serial is not declared. It will not be declared in this scope, obviously. All right, so let's start by actually Kybernetes mesh controller. Serial obviously will never be declared in this scope. USFS max. Battery low. I removed the interrupt there if IMU is connected. Okay, so I'll have it. So I have it setting up the IMU, but I don't have it doing. Okay, I'm just trying to remember how that worked. Okay, so channel A pin 2, 3. So that are the two non. Those are the two actual interrupt pins on the AVR. Pins 2 and 3, those are interrupt 0 and 1 input, so you don't have to use the pin change interrupt. What was using the pin change interrupt? It was just down here. Attached to pin change. Ah, the bumpers and the IMU use pin change interrupt. Okay, cool. We'll have to... Chibi doesn't actually have an implementation of pin change interrupts for the AVR. Looks like somebody started at some point. There's a couple of things merged, but it doesn't actually what do you call it? It was never. It doesn't look like it was ever finished. Okay, so let's start by creating ourselves our main these main function things that we have to do. So we're going to open the file of Chibi. Oh, sorry. Just a second. OS. No, sorry. Demos, AVR, nil uno, main.c. Cool. And so we're just going to lift this code out of here. So HAL and ch.h. We're going to bring those up into here. And then we're going to do our... We're just going to say we have one thread right now. I'll just copy all this fun stuff out of here. We will have more threads in the future. It's just, for now, let's minimize, the things that we do. So this is going to be primary. This is going to be, we're going to call this the main thread, just for now, because we don't have a better name. Main thread, working area, main thread. Main thread. And it's just going to call, we're going to call our standard Arduino functions of call setup. We're going to call while true loop. We're just going to delete thread 2. Although that SD start thing will be needed in a second. I'm going to call this main. What is this table thread? Is that a priority, or is that yeah, is that first thing a priority, or is that just a thread ID? ChibiOS. Working area. Let's try. Where is it? Thread table thread. Oh, priority. Okay. So I don't know if lower is more priority. Usually lower is more priority. Level. Oh, priority level for the underlying architecture. We're going to say, so main is 0, blinker is 1. I don't know if, I'll just say 0, because we don't have any other threads running, so, it's fine. Main, working area, main thread. Oh, yeah, and then main thread. Cool, we have now created the thread table. Location, entry point. Let's start all this internal fun stuff. And then this is the idle loop. I'll just leave that. Just don't sleep. Okay, and let's see what happens. Obviously, it's going to not be happy with us because of all of this serial stuff. Millis, not developed. Well, it didn't throw any errors at about the base of it, right? What if I threw an error down here, like something that's clearly wrong? Oh yeah, nice. Cool. So setting up our thread doesn't seem to have made it any more upset at us, right? So most of our errors, admittedly, are about serial logic, because obviously the Arduino serial class does not exist inside ChibiOS. But so we're going to need to deal with a replacement for the serial class. We're going to need to the replacement for the encoder. Need a replacement for a few things. The encoder, replacement for some of the like the bumper interrupt, and some of the timing logic. So We got our work cut out for us here. Okay, so let's start with the low-hanging fruit, the thing that'll solve most of our compiler errors here, and start with serial. Or getting the serial port back up. And let's see here. Wire set clock. Array speed. All right. Okay. So, yeah, let's do the low-hanging fruit. Let's start with serial. So, serial. So if we're looking at, with that, let's close all these other things here. So if we're looking at serial, so we've got this thing called activate serial driver, and then routes are using USART0. So something about this serial driver is obviously how we're going to be communicating on the serial port. So the existing logic that I used, like pretty much everything everything Arduino, it does what's called a super loop, which I have it basically in the loop. It figures out, it calls this controller update function, which I pass the current time to, and it figures out whether there needs to be an update cycle to the internal state of the robot. And then if, after it's done all that, it checks if there's any, serial data available, and then decides whether it needs to handle a packet. So, and then it'll only block, so what these handle configuration set things do, or the configuration set configuration get, these handle packet types, essentially. These will essentially break out early if there's not enough data in the buffer to satisfy the command. So let's see. So obviously, the way we could do this, in ChibiOS is have the packet receiver task. We could implement this such that there was a. So we're going to try to make the minimal number of changes to start off with, and then we'll start using ChibiOS features to make it more performant, or well, maybe logically better. I don't know if we can call it more performant, but. Maybe more, what do they call it? Idiomatic ChibiOS. Yeah. So, the ideal state would be, there's a packet thread that, sits, or a command thread, packet thread. There's a thread that sits there just reading data off the serial port. And then, when it got into, rather than doing this, oh, do I have an available number of packets? Oh, it's less than what I'm expecting to receive. Let me return it, and then somebody will come back to me later. What it could actually do is it could be like, well, okay, I know that I'm supposed to receive this type of packet, and then it just blocks that thread until the data is received, and then it'll process. Which is what it could do if we built a packet thread. Right now, I would like to just make a direct conversion if possible. So what we're going to do is look at, so ChibiOS serial driver is what we'll Google, and I'm going to just move this back over to give us a little more readability. Play embedded ChibiOS serial driver. That's 19. That's one of the things I've never really liked about these Doxygen docs, especially the versioned ones, is that Google, okay, it's not Doxygen's fault, but Google's, search engine, search is that, you'll look for a document and it'll be like, a bunch of versions old, but, and then, Doxygen itself, doesn't have a way to select the version that you're looking at through here. So, we can hope that, if we go to doc, chibiosforge.org, maybe if we go to docs like nil documentation, maybe that'll take us to a full reference manual here, kernel concepts, your modules, nil kernel, or looking at the HAL, right? Because the nil kernel, RT kernel, those are the kernel things. But in terms of drivers, that's down here. So serial driver, that's what we're talking about here. This whole SD put, SD get, SD whatever. Let's see, is there SD get, number of bytes in, get would block direct SD control. Can we get the number of bytes in the buffer? SD stop the driver, start the config, incoming data, handles incoming data, request data. Get would block. Bypasses the indirect access channel. Directly checks the input key is faster, but cannot be used to check different channel implementations. Okay, well that's also another thing. Serial driver implements uses IO queues for communication. It implements the ChibiOS channel API, right? Supposedly. What if we... Because there's this CH thing, that CHN right, HAL channels, right? Chan write timeout, Chan read timeout. Chan control. Can we even get the number of bytes sitting in a buffer for one of these channels? Is that a thing? I don't know, look like it. Message size, read, control, channel control. What types of channel control things can we do? Channel control, pointer to the derived amount of data to be transferred, number of ticks until a thing. Channel blocking read. Oh, that's channel blocking read, not control. Sorry, channel control. Control, channel, operation. What kind of streams? Maybe abstract IO channel. Base channel, right. Hey, here we go. Channel control. ARG. Devoted to base channel. Control operation code. Channel get timeout. Channel blocking read, byte read with timeout. Channel get, channel read. Stream read. Function reads data. If the data is not available, the calling thread is suspended. Number of bytes transferred. Okay, well, you know, it kind of looks like we can't actually read the number of... honestly, if I'm reading this right, it doesn't look like there's a mechanism by which to actually ask it the amount of data that's sitting in the buffer. Look, I mean, there's SIO, but I'll tell you now, this isn't implemented for the AVR. This SIO driver, only the serial driver is. So looks like SD async read, direct non-blocking read from a serial driver. Input queue, output queue. What types of control codes are there? Maybe there's a control code to get the buffer depth. That would be cool. Nope, invalid. Delegating LLD control. It's serial LLD. Okay. Knit stop. You know what's in here? Start stop. Well, where's that control function? What the heck? Didn't it literally say that it would call this control function? Which maybe doesn't even exist, like, on this device. Okay. Okay, so we don't have an option. We have to go with oh boy. So we didn't refactor this whole thing to use the IO thread, or to use a packet thread. Okay. That's fun. Handle set steering. How much of this did I write that could easily be thread safe? I don't know. As we start mucking with we start mucking with a lot of stuff in here. There's gonna be a heck of a refactor. Okay. Here, viewers 5. Fun. Fun. Yeah. This is gonna be a heck of a refactor. All right. Okay. All right. So we have to refactor all of this. I'm gonna wait. I'm gonna not do anything until we can't check the amount of data in the buffer. So while we could obviously just we could probably hack something up and figure it out, but if we're gonna have to go full, idiomatic, Chibi, we're gonna have to figure out which of these can be easily converted over to a more oh god because admittedly, some of these packet functions I mutate state of the controller, and that call update also can mutate state of the controller. But previously, those aren't concurrent functions. The one runs and then another one runs. They can never stomp on each other. So, but now I gotta have like blocking controller update. Now I'm gonna have to do essentially whenever controller update runs, I'm gonna like take a lock or something. All right, so let's figure where to start. It kills me inside that I have to deal with these squigglies. Thread table. Okay, and what include paths does this have that I can inject to make the squigglies go away? Okay, HAL OS. AVR demos OS HAL include OS Haman. So many includes. Fun. I mean, it found that. I don't know. Okay, whatever. We can deal with squigglies. Alright, this is all because I'm not including... that one's all, actually. I can fix those right now. I can include AVR/IO. Haha. Some of those will go away, right? These will disappear now that I included AVR/IO. Yeah. Hey, that's defined. Stop being mean. Alright, close it and reopen it. You bastard. Okay. Yeah. Yeah. Okay. Fair. Fine. I'll give it that one. We have to... Yeah, okay. Okay, fine. And do that. Compiler args. Hey, -d. That. Oh, well, or we just use defines. Now that should be defined. Yay, it's defined. Okay. Okay. Cool. So, all right. I've been saying that a lot, but I'm not necessarily looking for this. Okay, so we're going to create the comm thread, the communication thread. So we're going to do thread working area. Working area, packet thread. Packet thread. Do nothing for now. I call this 1 packet thread. Packet thread. Honestly, this doesn't have any higher priority. We'll figure out these priorities mean at some point. Come on. nil OS nil include. So we'll just add those. We'll just add squiggly. Add these as needed. Workspace folder OS or no ChibiOS / nil OS nil include. Right. That's where that's at. Right. OS nil include. Am I supposed to put semicolons on the end of those? Is that how this works? Is that what it was? No. I mean, even this freaks out. Table thread. Maybe that's what it's not happy about. No, that's in nil include OS nil include ch. Ch max threads is undefined. Oh, okay. Include fig / chconf. Maybe it'll be happy now. It is. Okay. This definitely includes stuff, but whatever. It's fine. It's fine. Are they going to freak out at me again? Yeah, it is. All right, fine. This is just to pacify this code. Okay. Perfect. So, that's all good. So serial, yeah. All right. So let's start with that. Okay, so we should probably... yeah. It's always the folly of switching. Okay. Sometimes there are patterns that you used that are not going to neatly map from one to the other. At least we're only dealing with 700, maybe 1,000 lines of code that we're having to convert to a new paradigm. This is still going to take me either all night or... this might take more than one stream. It quite possibly will. Communication. Okay. FCPU is undefined. I bet it is defined. It's defined right here in the make file. Oh, right. But the IntelliSense has no idea that it's defined, right? So now it's defined. All right. Let me go in here and make sure to add this build directory and VS Code and all this fun stuff to my gitignore, which I never had a gitignore. Okay, touch. Gitignore, right, because it was a Arduino project. Gitignore, I'm going to do build, dep, VS Code, right, yeah, there we go. Cool, don't have to worry about any of that crap. Well, I mean, we might want to include properties here, but it's going to depend on the platform, at least regarding the, where your AVR headers are. Anywho, add gitignore. Okie doke. So we've got our all old call Arduino setup function. You know, maybe we don't even worry about that right now. We'll just cut this up, right? What was the Arduino loop function? That probably won't even be meaningful here in a bit. Actually, we wanted 250k bit per second UART. Okay. Back to the make file. No. chconf. We want... Wherever I put 115, 200. Oh, halconf, right? Yeah. And put 202.3. Cool. And then the first thing we'll do, actually, we won't do that here. We'll do that in the packet thread. SD start, right? That's what we did, right? Okay. SD start, SD1. The default configuration is used. It was null, right? That's what the sample did, right? Null? Yeah, null. Okay. SD1 is unused. Alright. Actually, what we want is the OS HAL ports AVR. Oh, this is going to be a long one. Okay. That's a VS Code thing. HAL, or sorry, it's OS HAL ports AVR, and we're a mega AVR, right? Ports AVR ports AVR mega AT mega XX is one that we want to include. Include mega slash LLD for low-level driver slash USART v1. Okay. This should make things a little more happy. Cool, it did. And HAL source include. Oh, we did HAL source include, right? Maybe. Who knows? HAL. Wait, no, it's just HAL include. Yeah. Alright. There we go. Cool. Yeah. Anybody who's watching, feel free to interrupt me at any time if you have any questions. I'm here to entertain while also trying to fix my, while also trying to do this anyway. All right. All right. Attempt to entertain. Hope. Okay. Yeah, I'm just scrolling up and down because I'm trying to think of a place where I want to start poking, right? Okay, so we've started in the packet thread. We've got start. I don't want to add a comment to a function called start that says it starts something. No shit, that's what it's called. It starts something. Okay, start the thread. So we need to. Okay, so let's start going over. Okay, so the core function of a lot of these handle, I was trying to be clever with all of these, like, using C++ stuff and then using templates to auto-generate, the communication headers and things. So that's probably just about to bite me in the ass. So, so the way that the structure worked previously was, obviously, if there's no data available, there can't be any packet type. And then what it'll do is it'll check if there's any available data. If not, then it just aborts because there's nothing to check. Otherwise, it will then peek at the first byte in the buffer, because the first byte in the buffer is theoretically going to be the packet type. And then based on that packet type, and note that it uses peek, so it won't dequeue it. It'll just look at the first byte. So what it'll then do is check configuration, one of these handle packet something, functions. Oh god, these were ugly functions. Sorry, let me finish my thought before I come back to that. So yeah, so let's just take, for instance, handle packet steering set, because that's pretty self-contained. So then what it'll do is it'll check if serial available, which will again return the bytes in the buffer. It'll check if it's less than the transport size of that packet, which is something that I defined in this horrid attempt at making things somewhat generic. But either way, so I would always define how many bytes does this take on the wire to transmit minus a checksum value. I think, right? Send, transport size. Oh, right. Sorry, minus a checksum byte minus the packet type. Because there's a single byte CRC8 checksum sent at the very end. And then there is a packet type byte set at the front. So it's always +2. I probably could have abstracted that away better. But all of these are +2 because of that, packet type byte. And here we go again, right? Handle configuration, get is +2, set is +2, steering is +2, set PWM +2. There's all these +2s because it's packet type, checksum byte. Probably could have abstracted it better some other way, but I digress. So it would then, so it would check if there was enough bytes to essentially communicate this packet across the wire. And if not, it would return. And because it never actually read anything, those bytes stay in the buffer. Whatever bytes were there stay in the buffer. And the super loop that's coming around checking all this stuff, it's repeating that logic every single time it comes through a loop. But ideally, if it's in here, there's nothing else to do. So it'll keep coming through this loop until finally there's enough data to read that packet type that it's calling into here. Let me go back to where I just scrolled away from. So okay, in this case, command packet, receive a packet, and then based on the value that it gets from that, it'll then call a function, set steering. So steering set. Did we have enough data? If we don't have enough data to communicate a set steering packet, we return out. Otherwise, it's a command type packet. We then call a function to receive that packet, and then based on the data that we get from that, packet dot set steering output. Or sorry, the command packet is a set steering. I was trying to eventually make this where all these little handler functions were just a generic template thing that you use, but I never quite got around to it. Again, the code's kind of ugly in a lot of places. This is hobby code. I had a competition in 3 weeks, and I needed to write code that would make this work. And so a lot of this is written as I'm just going to hack on it until it works. Oh, it's working. Let me not touch it. The competition's next week. Or tomorrow sometimes, right? I think I remember writing the crawl function the night before the competition. But either way, so it wasn't really designed. I didn't really engineer this. I kind of hacked it together until it worked. So we're now attempting to come back and slightly engineer it, right? Apologies. Okay, so receive packet, do something with the data from the packet. Otherwise, and then the response would be, type is just a no argument acknowledgement, But I think no argument packet, set steering packet was my attempt at, essentially an acknowledge back to the host that packet was received. It just acknowledges, I think, includes a sequence number. I say but and so, but way too much. Okay, it's me, because nobody's talking to me, and I have to keep trying to talk to you guys. I just try to fill silence, but I just start making noises when I don't actually know what to say, right? So, but again, word salad. Okay, sorry. So it sets the steering, and then it tries to create a response packet based on packet type. Send the response. Otherwise, if this receive packet was false, and receive packet returns false if essentially there's not enough bytes of the checksum failed. So if the receive failed, which means there was an error, bad check, something failed about the function, something failed in reception, probably the checksum check. It just returns a negative acknowledgement, a knack. It's command packet send type. You tried to send me what presumably is going to be a steering set packet, but I'm saying I got it bad, and I'm including an error code of bad checksum. And then you send that response back over the wire. So what we're going to need to do is, rather than, so all of this receive packet now needs to be a blocking function, because when we read a byte off of the serial thread, we will dequeue it from the buffer, but so we will dequeue it from the buffer, but because we're in a thread, we can now safely block. We don't have to worry that we're blocking the thread because we have a separate thread that is handling the packet communication. When I originally wrote this was an Arduino sketch super loop style project where, if you spend time in a while loop here doing nothing, you will not leave. Like, the CPU can't do anything. Well, I mean, it can handle interrupts, but like it can't do any other logic while you're stuck in this while loop because it's a single threaded task in Arduino. We're now porting to something that actually has threads on an Arduino, on an AVR. I keep, for a long time, AVR and Arduino ended up being kind of synonymous because the first Arduinos for many, many years were AVR, Atmel AVR, now microchip AVR, but they used an AVR CPU, AVR microcontroller, and then I think the Do, the AVR Do, back in 2013. I can't remember what came first, the Arduino Mega or the Do. I think the Do came later, but the Do was the first non-AVR Arduino, I think. But either way, so if I may say the word Arduino, I'm writing Arduino code here. I mean AVR. So if anybody who's being pedantic, if I trip up, I am writing a ChibiOS AVR project or program that will run on an AVR based Arduino, in Arduino Uno version 3, which contains an ATmega 328 CPU or microcontroller. But if I jumble my words up, it's fine. If I say Arduino, I mean an Arduino Uno running an AVR processor. If I say Arduino coding or Arduino C, I mean C for an AVR for an ATmega 328P in an Arduino Uno. I know there are very, very, very many non-AVR based Arduinos now. There have been ARM based Arduinos for many years. I mean, the fact that you can now use Arduino for not Arduino products too, right? Yeah. But if you're starting out now, I recommend not using the Arduino IDE, using Platform IO or something. So what we're gonna do? So I think the easiest, lowest barrier way forward on this is going to be turning all of these handle functions into blocking functions, and then essentially this we'll go and we'll convert this receive packet function into a blocking function. And then essentially this will have to receive packet will attempt to receive bytes. It will call a blocking read. I will receive this specific number of bytes, and it will block the packet thread until that data is available. So let's start doing that. So the first thing that we're gonna do is, besides the fact we got all of these errors right here, right? So we did SD start. That should bring up our it'll bring up our serial port. And so what we're going to do here, so we're now going to go into the packet loop, packet reception loop. Maybe we convert loop just to try to make the diff a bit easier. We're going to convert this packet loop. This will become our packet loop. This becomes the packet loop. Or, we still got to tab all these damn things over. Nah. We'll just leave it where it was, just for the sake of the diff. For now, anyway. While true. Wow, while true. How Java of me. I'll just call this one packet loop. We're gonna define That as loop, and then void packet loop. Okay. I clearly have accidentally disabled my Git integration on this repository here, so I'm going to restart VS Code just for now. There we go. Hopefully that'll bring up, yes, I would like to configure IntelliSense. Sure, we'll configure IntelliSense. Use... Oh, I'm scared. What is that going to do? I'm going to delete everything I've already done on CPP properties. No, it does not. Thank gosh. Maybe it'll read my make files and do what it's supposed to do. That would be really that would be really sweet. I don't know if it's capable of doing that though. What is makefile tools? Index on workspace. Okay, whatever. Okay. We still don't have our Git project coming up here. Did I? Please tell me I didn't accidentally destroy my Git repo. That would really suck. No, we're still here. Cool. Why is my Git not working? Did I accidentally tell it not to trust this repo or something? That'd be really funny. Sorry, git diff. Oh, the diff's still going to be angry. Oh, I didn't break it. It's because I renamed the file. Okay. Okay, we're just going to commit this just to get git log commit -m start chibi OS refactoring. Oh, it's angry that I put stuff in ChibiOS. Okay, right, because I built the demo git status. Of course. All right. Untracked files, and we'll just say git checkout are on the sample. Okay, cool. Now there's no differences. Cool. What if I push that? Ooh, spooky. EA. What does that diff actually look like, you know? This commits ahead of main. Alright, anywho. Cool. Chibi. Cool. Okay, so we got our packet loop. This is our packet loop. We no longer have to say serial.available. What we're going to do is we're going to take this whole channel pattern. Ooh, interesting. There's some fun sensor implementations in here, looks like. Anyway, sorry. File list, modules, HAL, interfaces, streams, abstract IO channels. Okay, cool. So we're going to stay channel read, pointer to a data buffer. We only want to read one. So we're going to say packet type. Ew, no, stop. Type equals packet type none, right? Do I have a none type of packet? Knack. Oh. Did I really not? Wow. Did I really not define a null pack? I didn't. Okay. None. Cool. If you send a 0, it's none. Alright. Alright, so packet type none. Type none. Alright, cool. I'm gonna delete that. Packet type none. We're gonna say chan read sd1 type packet type 1 byte. I don't know if these functions could probably fail. Message T. Yeah. Chan read. Incompatible with the parameter of type. Of course it is. Interpret cast. We went to 8. Okay. Read 1 byte. What does this return? Read. It returns that. Read. Stream read. Read. What does that return? Size T. Returns the number of bytes transferred. The return value can be less than the specified number of bytes if the end of file condition has been met. Okay. So, if channel read less than 1, and return, because, you know, we didn't get anything. And hopefully we didn't get more than 1. So we're going to say not equal 1. Really hope it doesn't return more than 1. Okay. Not equals 1. Actually, we can just say size of packet type. Not equal size of packet type. It can be a little extra. Right. Actually, what? Oh, right. That's the function. Not equal size of packet type. Cool. All right. Then we return. Something went wrong. I mean, that should be obvious, but whatever. Okay. And I'll read. So, now we will go to all of these configuration sets. And what we shall do is something went wrong. No, shoot. Okay. Sorry. Something went wrong. And we're going to switch by packet type. Perfect. Okay. So now what we need to do is we need to go into one of these configuration set, for instance, configuration set. And then this whole serial.available thing needs to be command packet receive packets. Because this is the way this works. It reads the type, but this is why it's always +2. It was +2, right? Because we read a type, then read the actual data of the function, then we read the checksum value. So what we now need to do is we've already pulled the type off of, we already pulled the type. So now we need to actually go in and call receive packet. So this would be +1 essentially. We need to read the packet in. Okay, so what we're gonna do here is we're gonna be a little cheeky. So we don't need the type anymore. Actually, we don't need the type. We know the type because type was never checked, right? Oh well, I mean it was because it needed to be known. But we do know the type because we know we have the template we're being called with, right? So We have the thing. Sorry, we have the thing we're being called with. Let me just double freaking check again. Stop cursing. It's bad. Okay. Receive packet. Failure type. Command packet. Command packet is a disarm packet. Command packet. Send transport type. This is going to go by type. And go by. I believe receive type is the. Yeah. If packet type configuration set. Reference configuration packet send type is configuration set. Configuration get. Okay. I think I went and I did something silly like send type is from the host perspective. Or, well, I mean, that part's not silly, but I believe send type, if I recall, is from the perspective of the transmitter of the packet, obviously the sender. So in this case, it's going to be the Raspberry Pi. And then the receive type would be the response to the host. So like, for instance, status packet can't be, there is no, the host doesn't send a status packet, just the receiver would send status packet. Okay, so I believe the actual, quote, packet type from that we need to, or from the perspective of receive packet should be the send type. So let's just, for an instance, set throttle set PID. We'll go here. Throttle set PID packet. The send type should be throttle set PID, which is the same thing that called this, right? Throttle set PID. Yeah, okay. So the send type is what we need to vector on. So in this handle packet receive, well, I've lost it. Receive packet, cool. We're gonna say we can delete this because we already popped it off. What we then need to do is CHN read. This is gonna be serial driver 1. Actually, you know what we could do? We could make this even better. No, we're not going to touch that for now. We could pass the serial driver to the receive packet function, but we won't do that for now. Channel read SD1. Actually, sorry. Just 1 minute. I need to take a quick call. All right, apologies, I'm back. All right, so yeah, I mean, technically we could have the receive function here take this channel read, or take the serial driver pointer. I'm trying to think. Channel read. What? This is, I mean, realistically, this is a what kind of or unit 8 IP size the pointer to read. Okay, I mean that's my own implementation. Sorry. Virtual memory table. We're gonna go here. Stream methods. Ooh. Void. Oh, lovely. We just passed it a void pointer. Perfect. Anyway, so in the future, yeah, we could pass, but the Uno only has one serial port, so it's not that much of a loss. I mean, we can change that in the future. Famous last words. Okay, channel read. We need to read. This is the bytes, so we're going to do a reinterpret cast. Uint 8 underscore t. Packet, just like that, and then t. Send transport size. All right. If channel read not equal t, send a transport size. And something went terribly wrong. Return false. All right, now we need to read the checksum. As we do checksum, should calculate CRC8 data. Uint CRC8 pointer to the data. Sorry, that'll pass by value, that'll pass by type. Okay, well, just to make things a little easier, uint 8 checksum is 0, and then we do a chan read sd1 reinterpret cast. Actually, ironically, this is already a uint 8 checksum 1. And we do if not equal 1. Something went wrong. Return false. Cool. Nice. And then we do our CRC checks as we did before. And then cool. So we can do a send sync packet. We'll just replace serial.write with chnwrite. SD1. Do a const auto. Packet type is packet type sync. We'll do a packet type. Size of packet type. Oh, we're gonna do our good old friend reinterpret cast. Because we are modifying the type. The Rust programmers are screaming at me right now. Okay. chnwrite. Alright, and because this is, I made it const, it's freaking out. Okay, yeah, auto packet type. This channel write really should take a const pointer. Does it really not take a const pointer? It does. What the? Oh. I need to do const uint 8. There we go. Okay, that was just my bad the entire time. Cool. Where does it think this wire class is going to come from? What is it? Oh, it's because these are all templates that it's not actually throwing an error. Yeah. Okay. Send sync packet. So yeah, let's also. Yeah, this is gonna have to be rewritten to this get struct from wire. Okay. So we do something went wrong. Yeah, so calculate CRC, then we do our checksum calculation. Oh, but we did delete because we have that would have screwed us over. Okay. We're supposed to mix in the type, but obviously this type value doesn't exist anymore. So we're going to say, I did declare this const. I did end up declaring a const. Okay. So checksum const uint 8 underscore t type equals t send type. Alright, CRC8. Cool. Actually, you know what? I think Yeah, I mean, a proper checksum, I think if you include the checksum byte in the calculate, it ends up being 0. So I could experiment with that at some point. Let me just move this back up to where it used to be. Okay. Okay, cool. Const type is send type. Perfect. Perfect. Okay, that should work. So we do const type is... Oh, look at that. Const u int 8. Perfect. Okay. So we'll do that with this same concept. We will do our chn write. Actually, I'm getting distracted. Actually, what we can do here is chn write. Rather than calling this so many times in a loop, what we could in fact actually do is, if I want to transmit 16 of these packets, I could say const uint 8 packet equals 16 equals packet type sync. I don't know if there's a repeat function in C, but either way, sync. Sync. No, alright. I'm too lazy to do that right now. Alright. That would be really... I mean, that would be ideal, but sync packet is just 255. Does channel write take... Can this take progma pointers? That would be cool. Probably can't. But, okay. Anyway, yeah. Rather than doing this, nah, I can't be that lazy. I can't be that lazy. Const uint 8 underscore t packet equals... We'll just do this 4 at a time. Sync. Const auto. Why not? Reduce auto. Oh, right. Oh, top level array, of course. Uint 8 underscore t. Fine. Uint 8 underscore t. Alright. Okay, packet type sync. Okay, cool. I'm gonna say packet size of packet. Get rid of that. And we don't actually need the for loop anymore. We just do that. That should be 16, right? Yeah, cool. Cool. All right. The synchronization packet. All right, so back up here, we replace this bottom logic with our channel write. So if channel write SD1 type size of type, okay, come on, it's 1. Not equal 1. Something went wrong. Return. Well, I mean, void. Return false. Alright, something went wrong. Yeah, including all this channel 1 stuff is kind of bothering me. Okay, stream right. IP. Is this going to be... Let me base sequential stream. I think, right? I mean, and honestly, type name S. We really can just do S. We really can just do that, you know, stream. Send packet. Run. Actually, no. That should be channel. Yeah. All this chan. Cool. There we go. Channel. All right, something went wrong. And we need to do our, so we wrote our type. We need to write the packet. If chan write channel reinterpret cast const uint8 pointer packet t receive transport size not equal t receive transport size. Then something went wrong. Return false. All right, and then we calculate our CRC, and then we do that. We can just return chanwrite equals 1. Eek. Hold on. C8, channel write, channel type. Yeah, so then we can delete. And say packet, receive transport size. So yeah, then we can just delete that stuff. Write the type, write the contents. Write the, no, ooh, almost messed up, CRC8. Write the CRC. All right, something wrong. Yeah, there we go. Return equals 1, equals 1, channel right. Perfect. Okay, so those are generally ported. All right, so next we just go to packet, no instance, okay. Yeah, so all of these, oh boy, we just introduced a lot of fun little errors. Okay, so serial.read, so we're just gonna say chan read underscore t discard oh, this is probably just SD read. Is there just an SD get? Is that a thing? SD get. Yeah. Cool. We just do SD get. I think, right? SD get. SD1. That's a thing, right? Yeah. Actually, you know what? Maybe we should have just done SD get. Cannot be used as I get Q get timeout 0. Does this block? What happens if we call a read with a timeout of 0? Is that blocking? Is that non-blocking? Channel blocking read, stream read, channel read timeout. time infinite. What is time infinite? Sys interval -1. Oh. And time immediate is probably 0, right? Yeah, okay. So, no. SDGet does not return... Well, actually, we don't need to. Sorry, serial.read here was to discard this unknown packet type. We don't actually have to do anything. Because we've already dequeued it. We don't need to read another byte. Okay, cool. We're good. And now what we can do is we go through all of these, and then handle sync. We don't have to because we've already read it. Send sync packet. And then IMU update. We do SD1. And then every time we see an SD1, we say SD1. SD1. We can delete the availability check. We can go SD1. Ah. You know, let's just copy this little bit here. SD1, SD1, SD1. Delete serial.available. SD1, SD1, SD1. Delete serial.available. SD1, SD1, SD1. Delete serial.available. These are some of those things where it's like I'm gonna have to get a lock on some of the hardware. SD1, 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 SD1. Delete the availability. Check. SD1, SD1, SD1. Delete the availability. Check. SD1, SD1, SD1. Oh, controller update also calls a send. But, alright, that's fine. SD1, serial.available. No more serial.availables, right? I don't think so. I don't think so, yeah. Let's call make now. See what happens. A lot less errors. Cool. Now we just have a lot of errors about wire and encoder and digital read, which makes a lot of sense because we haven't ported this yet, and so encoder is going to have to be a little clever. Wire was not declared in the scope. Use entropy check. All values yield to 0. Okay. That's gonna be one of those. I'm gonna build it when it's finally fully working and pray that it works because we're changing so much code without even being able to test. Ugh. Okay. This whole thing, we're not gonna prevent us from mixing this stat. Okay. Ugh. So we're gonna need to do our IMU update. Go to definition, IMU next update. Oh yeah, we don't really want to spend the time to. We don't want to turn on the IMU if we don't have to. At least not yet. Because I bet this USFS Max thing is going to be real upset at us. Because it's going to be based on the wire class. Oh yeah. Oh boy. Oh boy. That's going to be real angry at us. Actually, you know what? For minimal testing, we'll just disable the IMU for now. Yeah, it's if we make -J, it should, yeah, because UFS Max is going to be real pissed. Okay. It's actually, yeah, we'll get there. Okay. Alright, we're gonna do digital reads. So that's, so let's now do, so I mean, we haven't fully finished fixing the serial stuff yet, because we're gonna have to add a lock around the control, because, or sorry, we're gonna have to add, anytime that we need to touch state, we're gonna have to add a lock, because we have to make sure that we synchronize on some of this stuff. Or sorry, two threads could be both. You know, the previously the serial handlers could sometimes manipulate state, and also that controller update could manipulate state. And one was run after the other before, which meant there was never going to be a race condition. But now, because they're on two separate threads, there absolutely can be and probably will be race conditions on state. So we need, you know, let's just do that now. So how do we handle mutexes in ChibiOS nil? Nil kernel semaphores. Let's do that. Yeah, semaphore object init. I'm gonna do semaphore T must be non-negative. For static semaphore initializer with no need for chsem init. Perfect. I like that. Okay. So up here with all of our freaking giant shared state shenanigans, let's say semaphore decal state semaphore n. So we have a default of 1, right? Alright. Static semaphore initializer. Statically initialized semaphores require no explicit initialization using sem init. That's what we want, right? I think. chsem init. chsem. There's a signal operation that increments the lock, right? Signal I syslock. Yeah, right. Debug check ++ semaphore count. Okay, hold on. plus plus count less than or equal to 0. What? Hold on, ch7 init. I mean, it wouldn't make any sense to have it not be 1. It's some signal. There's a signal operation of semaphore. Should increment it, right? Right? That's how this works, right? Wait. How the invoking thread has been released from the semaphore. Reset. On negative. I mean, sem signal. New value of the semaphore counter. This value must be non-negative. Doesn't reschedule if. Okay, I mean, I'm curious. Some signal. Plus plus. Less than or equal to 0. Hold on. This value must be non-negative. Alright, hold on. You know what? Fine. ChibiOS, semaphore, initial count. I just want to make sure I got this right. Semaphore is taken, and there are queued, and can be taken before a sem wait would block a thread. Okay. So okay. Okay, so let's look at sem wait just to make sure that we understand. Sem wait. Let's check this. Sem wait. Note, sem account of volatile variables are manually optimized. If it's less than or equal to 0, then we obviously do that, then we have to sleep. If otherwise, decrement by 1. Okay, yeah, so if we start the semaphore with a count of 1, the first call to semaphore wait will succeed. Second call to semaphore wait will block. Okay, perfect. That makes me feel better. Okay, semaphore decal state semaphore 1. Okay, cool. Let me just make sure that that little tiny bit builds. Looks like it does. Okay. So controller update. The entire freaking thing is gonna take a lock on the state control. But what we need to do is we need to build ourselves a little tiny locking utility so that so what we're going to do is we're going to copy a bunch of code out of the balancer, or not a bunch of code. We're going to copy a piece of code out of the balancer project that we did before. We're going to use that RAII lock thing that we wrote, which is honestly one of the simplest freaking things. It just takes a lock in the constructor and releases the lock in the destructor. So if we take that balancer code, we go to that utils class that we'd written for it. Yeah, and take this scoped lock. I'm gonna paste that in here. Except in this case, it's gonna take a cool. Wow, I'm really bad at this today. Okay, hold on. That goes here. Template. Template. Type name. Sem. Sem. Pointer. Semaphore. Right, we'll just call it mutex because that's what we did before. Yeah, before we shove it in here, let's just make a new file lock.hpp. Let's say if indef lock hpp define lock hpp and if lock hpp. Go back to our motion. No, Kybernetes. Take this lock. Do in here. Gonna paste that. Okay, so scoped lock. Let's just change all occurrences to lock. Okay, mutex. Change all occurrences to sem. Change all occurrences to sem. All right. And we're gonna replace this with sem wait or ch sem wait on sem, and then we're going to say sem wait forever, right? It'll include sem wait time infinite. Yep, sem wait, just sem. Cool. And then if sem sem signal. All right. Wait, sem signal. Perfect. That should do us. All right, cool. We're going to include. So the whole point of that class is basically if you create that struct, or you create an instance of that class, that lock type, and you give it a semaphore, and in the constructor it will take the lock and the wait on it. And then whenever it is destructed, it will then free the lock. And so that just helps us because we have these functions that it can return in multiple places. So it just makes sure that if you leave the scope, if the scope dies, the lock's freed. So because we did that, because we had the semaphore, we're including the lock. Kill switch types. Whatever. Include lock. What we're going to do here is we're going to say set throttle, remote command. We're going to do update, control update now. All right, cool. So we're going to take a lock of. I didn't even call it controller mutex. I called it state semaphore. Yeah. of state semaphore. Cannot deduce. Fine. So we're going to take a lock on the state semaphore, which will prevent us from doing anything nasty. And then in here, we've got receive, send packet, config. Yeah, but the fact that we're touching... Receive packet, handle configuration, get. All right, no, so we're good on this. We're not touching the state. Receive packet. Actually, technically, we want to do a lock on state semaphore, because we're reading this configuration structure. Although realistically, the configuration structure, whenever configuration default. Yeah, I don't think anything ever sets the configuration structure other than this command packet. But just to be safe, we're gonna do receive packet. We're just gonna lock it because why not? Might as well. And then, yeah, PID set tunings, response packet, and packet response. Yeah, we can do a lock. Configuration packet. Yeah. Okay, we don't actually have to hold the lock that long. We do need to hold the lock to send. Oh god, I hit the up key. Where did I go? There we go. Okay, we do that, and then in here we do the shit steering. That uses configuration packet. So, set steering. So we do a lock. And we'll need to make this better moving into the future, but just for now, just so we know what we're doing. Yeah, like this is a big one that mucks with state. So what we're gonna do is we're just gonna put a big old fat lock right up at the top of that. State semaphore. Handle throttle set PID. Another big ol' modify internal state thing. Handle packet crawl, another big ol' modify internal state thing. And send packet arm. Send remote command. Actually, I don't think that one actually touches state internally. Cool, we finally have one that we don't have to send a lock. Send remote command. But, yeah, actually, yeah, send remote command. Don't actually have to lock on that one. Nice. All link. Nope, cool. You can keep alive, receive packet, send remote command. Oh, actually, wait. Local state. Oh, no, we do. Because we're checking local state. So, we do have to take a lock. Because we might muck with local state. And yep, we're going to check that. I'm going to take that here. State semaphone. Ah! Alright, hold on. Change. Semaphore. There we go. Okay, receive packet. Send remote command disarm. I don't think I touched state. Okay, finally, here's one where I don't muck with my state. Reset odometer. Definitely gotta take a look on that. Oh yeah, now that's wrong. Okay, state semaphore. Odometer. Send sync packet. Cool. Okay, nice. Definition. Send packet sync. Channel right. Awesome. Okay. I think we have taken the lock in the places that we needed to take the lock. Okay, cool. What have we unintentionally... Oh, yep. Oh, I goobered it. Hold on. That's why I couldn't deduce the type, by the way. Okay, it's because I forgot. I goofed that. All right. Shouldn't have any problems now. Now, actually, all of the semaphore T stuff should be able to be deletable. Change all occurrences. Now it should be able to deduce type. Yes, it can. Okay. Okay, so the whole type deduction thing was if... oh, wow, I'm sorry. Type deduction. So if you have a template argument such as this, like type name semaphore in this case, if you have... essentially, if say that template parameter is used in the as a constructor parameter, the compiler knows that whatever type that you pass into the constructor is equal to whatever the type in this type name is. So you don't actually have to specify it manually, because you could do what we did, where we said lock semaphore T, so it's defining sem as semaphore T, and then it's known. But the kind of the power of the whole inferencing deduction system is you don't actually have to write that if the compiler can figure out what it's supposed to be anyway. So we're just gonna delete that because I mean, it can look cool. It could. I mean, it depends on if you think it looks cool or not, I guess. But lock state semaphore. So all right, cool. All right. So what's left? So we got the encoder, the wire, timing functions, setting pin modes. Okay, so for now, let's handle the wire stuff, because I think that's the next lowest. It's not the lowest hanging fruit, but I think that'd be a fun little thing to go futz around with. So wire.requestFrom needs to be replaced with the ChibiOS I2C logic. So we can go into config here, and I think I2C might be disabled by, MCU config. I think I2C might be disabled by default. Yeah, here we go. Change that to true. Cool. Now we have I2C. And now we can come into our... Previously we were saying, wire.begin. We can say... well, actually, you know what? Let's see. Halconf I2C, use I2C. Is that the use mutual exclusion true by default? How do we enable I2C at a certain speed? All right, so modules, HAL layer, normal drivers, I2C driver. All right, cool. I2C init, I2C. I don't think we actually call this. This is called implicitly invoked by HAL init. Cool. So we just need to call I2C start. And config needs to be set because I don't think there's any sort of automatic ability for config to be read from something. Right. Okay. Yeah. It's not like the serial driver. We have to pass an I2C config. Cool. All right. So what we can do is that's defined by the low-level driver for our platform. And so what we can do is we can come in here and theoretically we could say const i2c config equals something. And we can go to our i2c config structure, which isn't going to be set because we got to go to the one for the AVR. So that's going to be in ports, AVR, mega, LLD, I2C, .h. Which is going to be commented out because all those little defines that we did in MCU and all that doesn't get pulled into IntelliSense. This is all going to be grayed out for painful. Okay, so I2C config, so HAL I2C config. All it says is clock speed. Okay, so the only thing that we need to worry about setting is clock speed. So dot clock speed equals, well, we were using 100,000 before, so we'll just use 100,000 again. Oh, not a pointer, just clock speed. And then we'll say I2C start. I2C1. Is that a thing? Maybe? Or is it I2C1? I2C1. We'll see what happens. Wire. Wire.set clock is bad. Raise I2C speed. Okay. How do we reconfigure the I2C peripheral? Can we even do that? Not API. Can we I2C reconfigure? Is that a thing? Is that a thing we can do? I2C driver. Maybe. Who knows? Referenced by BMP085 start. Complex driver peripheral. Okay. Check that out in the future. Okay. But, okay, well, if we comment that out, it doesn't look like 753, 719. Okay, so I2C config didn't exist. So maybe we have to include it. I mean, why wouldn't we have to include it? But go to HAL, board. That's fine. HAL conf. Okay, fine. Of course. HAL conf. Obviously, it's driver late inclusions. I mean, it should include. It should be including I2C. What goes on I2C? HAL I2C LLD. Config. That should have worked though. Thank you to everybody. All right, yeah. Everybody who's watching, thank you for watching the stream. If you have any questions, just feel free to bug me at any time. I do try to keep my eye on the chat. And so, but what let's see. So, I2C config. Did you mean PAL config? No, I did not. I meant I2C config. I2C config. Yes, struct driver. Yeah. Come on. I2C start was not declared in the scope. I must have not enabled something here. Where's Hal conf I2C. Hal use I2C. Oh, oopsie. So I enabled it on the system, but I didn't enable it in the HAL. Okay, that is why that didn't work. Okay. And now it should compile. Well, other than me not getting the I2C driver name right. I2C D1. And what we now need to do is, in order to get the squigglies to go away, this can be fun. There's halconfig.h. Channels, streams, main, kills. If not defined, define it as true. I mean, come on. Oh, it's just complaining about that specifically. Okay. Because it is not including the right HAL, because okay. We have to add more things to our CVP properties. LLD I2CV1. And now this should be happy. Yes, now it is. Okay, cool. Perfect. So we've got that, and because I wonder, we got to raise the clock here at some point. So I gotta figure out where do we actually IMU start send sync, and it doesn't really send sync update. Well, realistically, this should be able to be set to 400 immediately. Okay. I2C start. To do check if we need to start at 100 kbits per second. Because we do end up in 400 kbits per second. Okay, cool. Perfect. So we got an I2C driver now. So let's go replace all the usages of wire with the wire dot war dot wire dot. Where is wire dot read used, or wire dot anything really? Begin remote transmission. Okay, only in these spots. Okay. So what we're gonna say is how do we use an R2C? I2C master transmit. I2C driver. So master transmit has transmit buffer, transmit bytes, receive buffer, receive bytes. Okay. So the way that works is that it starts transmitting to an address, however many bytes you wish it to transmit. And then if receive buffer is not null, then it transmits a repeated start condition so it can start reading. Basically like classic I2C EEPROM style protocol, like every I2C device seems to use. So we begin the transmission with the kill switch address, and then we write the command. And then we just write the 1 byte, and then we end transmission. So realistically, all we have to do here is what does this return? I2C master transmit timeout. 7 bits without the read-write bit. Kill switch address is 8. Let's see. Arduino wire class. I don't know if this is the 7-bit address. So this is 7-bit address without the read-write bit. I think the wire class does use the right bit. Both 7, 8 8-bit versions of I2C address, 7 bits and 8 determines if it's the wire uses the 7-bit addresses throughout. Okay, perfect. They are, the address format is compatible. Perfect. Okay, so we're going to be able to do I2C master transmit. I2C D1 kill switch address. Transmit buffer is command. Size of command. Null putter. Null putter. Perfect, right? Perfect. And it returns the operation status, which if it's not okay, message okay. Then we gotta return false because something went wrong. But actually, I mean, we're good overall. So return equal equal. Okay. Ah, damn, it doesn't fit. Okay. Turns. Okay. Perfect. I think master transmit acquires the bus. Gains exclusive access. But if the bus is already being used, then invoking thread is queued. Okay, well, fine. We can do it that way. I2C acquire bus. I2C D1. Alright, cool. Now we're good. Gain exclusive access to the bus. In order to use this, I2C mutual exclusion must be enabled. Okay, awesome. Cool. We do want to do that. Perfect. Send remote command acquire bus, do the thing, release the bus, do the thing. Alright, perfect. Because send remote command is going to be used by our handle packet. So our packet thread calls send remote command, but never our update thread. So that's perfect. Okay, sorry. Yeah, so that's perfect. Right, so now we're gonna work on our wire class. So we are going to start with wire.request from an address. So that's get struct from wire. So that sends a. So this is just a read, I guess. From size of t+1 request bytes. Wire dot fill the thing, checksum, size of t checksum, get the check. Okay. Perfect. Maybe. Okay. So we're gonna say that we're gonna do an inline struct declaration of. Oh, we got t object, so we gotta. Okay. So we need to do object. Okay, we need. Oh, okay. Maybe we can do dynamic typing. Actually, it's a template, so it's not actually variable length array. Okay. So that's struct. No, not struct. What am I doing? Sorry. uint 8 underscore t rx buffer. Buffer. Size of t. Size of object. plus 1. Okay, fine. Size of t plus 1, because we know that works. So then we do master receive timeout. So then we're going to do auto, we're going to do I2C acquire bus to CD1. We're going to do auto ret equals I2C master receive from I2C D1. And the address is address as we were passed. And then the buffer pointer. And then size of buffer. I2C release bus. What does receive? Receive one or more I squared C. Errors can be retrieved using get I squared C errors. Okay, well, we don't really care too much. We just care that an error happened. If ret less than ret not equal, message okay, then we're going to return false. Otherwise, we're going to check the checksum. Buffer, and then we're gonna, because we did it this way, then we're going to we're gonna check the buffer. Sorry, we're just going to do that. Checksum is going to be this last byte of buffer. Okay, so if we fail to receive, we just kick the thing out. Okay, so then we do if checksum not equals calculate CRC8 0 buffer. Actually, there is no checksum yet. So sorry, if buffer size of buffer minus 1 not equals buffer size of t, then return false. All right, so if ret not equals okay, or if the checksum is bad, if we fail to receive it, the checksum is bad. Okay, I mean, that's pretty self-evident, don't you think? Do I really need to put a comment saying if the message wasn't received or the buffer checksum doesn't match? Do I actually need to put a comment there? Does this code implicitly tell you that, if the checksum doesn't match, there's a buffer not equals calculate a CRC, and if ret's not equal okay, clearly something went wrong. Yeah, but now we need to do memcopy destination is there's our reinterpret cast uint8 pointer to our reference to object buffer size of t, return true. Okay. I really would like just to receive directly an object, but this API makes it not quite so friendly to do that. Okay, ret, yeah. How does this wire stuff look now? Wire stuff looks good. We're getting closer to not having any errors. We now only have 1.5 pages of errors instead of half errors. Okay. So, continuing along, we need to call this controller update every 20 milliseconds. Do I use that now function anywhere else? Controller next update. is that actually used anywhere in here other than to run every 20 milliseconds? And the answer appears... Okay, hold on. That now function. Okay, let me just search for now. Used it 9 places. IMU update now. Current time. Now. Alright, so it's not actually used anywhere inside of this controller update function other than to guarantee that it runs every 20 milliseconds. So, what we're going to do... We're just going to skip that. Controller update. Take a look on the state semaphore. Perfect. Hi. So now, don't worry about now. Don't worry about now. Chan. Oh, sorry. CH thread. CH sleep. Milliseconds. 20. Yay. Hi. And we have to figure out all this IMU stuff that we want to do, potentially, maybe, or not at all. And then now, if controller next update minus now equals the thing, prevent us from missing the next status update. I mean, we're doing async stuff. Like, it doesn't take us that long to send the R. Okay, you know what? I don't actually think that's much of a problem. Digital read obviously is a problem. Encoder is obviously a problem. All this pin change interrupt stuff is obviously a problem. Millis, controller next update, IMU next update. We actually want to do these updates on interrupts and not actually use a timing loop. So we're actually just going to delete that. I'm also going to delete IMU. Well, we'll leave IMU start just for now, you know. We'll have an IMU thread that reads the IMU eventually that is going to be triggered by an interrupt. But we're not quite there yet. We'll also need to use the ChibiOS. Eventually, we'll use the ChibiOS. What do you call it? Threading. Sorry, the ChibiOS PWM driver to replace this stuff that we're doing, the fast PWM to drive the servos. We will do that at some point. But, all right, now that we did wire, we're going to leave encoder for last just because... Okay, hold on, actually. This next update stuff can be deleted because we're not using a timing loop anymore. Pin change, rising, IMU next update. We'll just comment that out. We're not using it for now. We'll just comment it out. And then actually, yeah, we'll just comment out all of the IMU stuff. I don't want to deal with it for right now. UFS max. Max types, and then we're gonna just motion controller types. UFS max types. I think that's fine. Okay, yeah, we don't actually have to worry about that. Go back to our make file here and just remove that for now. Okay, cool. Almost. We're getting there. Oh, wait, where's IMU status? Status.imu status. Oh, well. I'm not going to deal with IMU status right now. All right, cool. So we need to configure. We're getting close. Okay, so let's do. Getting real close. Okay, so the last thing is really encoder, and some of our freaking pin change logic. Bumper contact is an interrupt that sets bumper contacted. If reading that is a thing or contacted, then local state is the thing. Bumper contacted is false. Oh, right, because the bumper pressed. Right, because bumper contacted stores that the pin's changed. Because if we basically this is checking this will read digital read to see if the bumper is contacted. But as this only runs every 20 milliseconds, bumper contacted will be true. Like if it bounces, if it clips, if it hits it and then it unhits it. Bumper contact will stay true because it's interrupt driven. Because this does only run every 20 milliseconds. So this just debounces essentially. Make sure that if it ever got clicked, it is in fact set. Okay. So all right. So digital read. We need to replace digital read because that doesn't exist in Chibi. So let's do that PAL port abstraction layer, pin abstraction layer, PAL toggle pad, something like that. Okay, what other PAL stuff? PAL set mode, set pad mode, port. Oh yeah, we're actually going to have to map. We have to map these Arduino pins to the actual. The Arduino pin to the actual underlying AVR pin. So let's pull up a Arduino Uno R3 schematic, just so we know which pins are which. That's a crusty schematic, but this is the official one. Okay. Cool. So, how does IO port to... What does that actually map to? Generic port identifiers. Interesting. Maybe this is part of the board config? No, maybe boards. Uno, port line, val, port D, B, something, port B. I don't know, man. All right. IO port 2. What is IO port 2? Okay, ports. Sandbox. Alright, well, we got a board. PAL line IO port 2 5E. So IO port 2 is clearly port D. But who's deciding that IO port 2 is DDR-D versus like port C? Somebody's making this decision. Ah, here we go. If defined, PAL config, it'll be IO port 0, 1, 2. So, all right, this is how it works. Okay, I see, I get it. So, we still need to know the individual pins, right? So, okay, sorry. Okay, so, encoder pin... Go to channel A, const expression. We gotta do this. Const expression, uint 8, something, honestly. Auto, encoder, channel A, port equals IO port 2. Const expression auto encoder channel B port is IO port 2. The pins on these are going to be this PD, well, 2 and 3 really, because PD 2 and 3 come over to what? Oh, sorry, that's not the 18 mega 30, 328, 328. Okay, yeah, so basically 0 through 7 on the Arduino is port 0 through 7 on the chip. Yeah, sorry. IO port 2, port D, is IO 0 through 7. So if it's in the lower 8 pins, it just translates. So, okay. So we're going to do IO port 2. So we can come down here. We can say PAL set pat cell line mode and pat cell port mode. Huh. Maybe this gives us a little more idea. I'll toggle pad. Oh, that's definitely not our processor. All right, so let's go back to the PAL driver. Port obstruction layer, IO port, LD init, obviously do stuff. Pad event. I wonder if there's pad event implemented. Well, that would be how you'd implement. I mean, that would be where the pin change interrupts would be if they existed. So we did OS HAL ports AVR. There's a PAL driver, GPIO. They don't implement pad event. That's sad. Okay. Never mind. Okay, so port LD init. Set PAL set group mode, PAL set line ID. Make a line identifier with a given port and pad parameters. Oh, that's cool. Interesting. Set line, PAL port line, read line, set pad. Oh. Well, that's cool. Line led on PAL line. You know what? That's neat. Hold on. Maybe we do that instead. Define encoder channel A line as PAL line IO port 2. Oh, I like that. B line is 3. Ah, alright. I get it. I think I get it. Maybe. Okay. So we're going to say get rid of these two. These need to be inputs, but not pull-ups. So we set line mode. Hey, okay. Encoder, channel A line, PAL line, PAL mode. Input pull up. Oh, sick. Okay, cool. So PAL set line mode, encoder, channel B line, PAL mode, input. Nice. All right. Nice. And then it's the same for the bumpers. Define encoder. No, sorry. Bumper a line as PAL line. IO port 2 4. Define bumper B line, PAL line, IO port 2 5. Nice. Let's do the rest for all these other ones too, except for the steering and throttle pins. I don't think those are going to actually do anything. Yeah, still put server defined. Okay, define IMU data ready line, PAL line, IO port 2 6, and define battery low line as PAL line, IO port 2 7. Nice. Really hoping we get to testing this before I need to go to bed. Okay. We should. Alright, cool. So we're gonna get down here. We're gonna say PAL set line mode, bumper a line, input pull up, PAL set line mode, bumper B line, input pull up, PAL set line mode, IMU data ready line to PAL mode input, PAL set line mode, battery low line, input pull up. Perfect. All right. And then just for now, we're going to disable these pin change interrupts. Expected a... Oh, oops. I wasn't supposed to put... I wasn't supposed to do that. All right. Cool. Now how much bad do we make? Getting pretty close. Digital read. Let's say PAL read line, right? PAL read line. PAL read line. Yep. All right, nice. Read line. Cool. Getting closer. No more digital read. All right, we just need to deal with the encoder, and then we're done. Okay. Well, not done, but we're getting there. Aye. Aye. I still haven't tested any of this yet. Oh man. Okay. So encoder quadrature. Yeah, it's 9:30. All right. Quadrature encoder driver for Chibi. I mean, somebody's probably written one of these at some point. Who knows? List. Somebody's got to have written a quadrature encoder thing that we can use. Or not. Okay. QEnc. You know, Hal Q. QEnc. Hal Enc. Hal something. Right? Enc. No? Alright. We gotta do our own quadrature encoder driver. Okay. Cool. So let's see. We gotta do quadrature encoder. What does that mean? We need to figure out how to. I also need to refactor this into some drivers at some point. But what we're gonna do. So this encoder class would be read. We'll comment this out because obviously can't use it. Read and reset, and it counts the number of ticks. So the way that these work, quadrature encoder, they basically have. So if you think about ticks, an encoder. There's some kind of mark that it's reading. There's a sensor that reads whether that line goes over it. So it generates a pulse train. Up 1 0 1 0 1 0 every time you pass the beginning and the edge of the little mark. Usually these are done optically. There's either a disc with holes cut out of it, a sensor's being blocked by the it might be one type of sensor would be there's a disc that has physical holes cut in it. There's a little optical sensor that goes through it, or that basically has little forks that go around it that the not cut out bits interrupt the light beam. So that's one way of doing it. You might also have a disc with white and black marks on it that there's a reflective sensor that reads. Sometimes it's done magnetically, like there's a little magnet that spins and you'll have either the north or south pole of the magnet flip. But the way that a quadrature encoder works is that there's a second sensor that is 90 degrees out of phase. It's called what's 90 degrees out of phase with the initial sensor. So basically what'll happen is, and this is actually a good illustration of what's going on here. So on, we don't even have to worry about this channel Z thingy. Basically, this pulse train of one, pulse train of another, 90 degrees out of phase. So in the middle of the pulse of one, so ideally they're 90 degrees out of phase. So at the middle of the pulse of one is when the beginning of the pulse of the next one is. And so what'll happen is if you see the rising edge of A before the rising edge of B, it's going one way. And then if you see the rising edge of B before the rising edge of A, you must be going the other way. Because if we go forward here, we see A, then B, A, then B. If we're moving the other direction, we see B, then A, B, then A. So you can tell what direction the motor is spinning in. So I connected the encoder inputs to the two interrupt pins of the Arduino Uno. Now, the Arduino Uno does have what's called pin change interrupts, which means that there is a single interrupt that is fired per I/O port when a pin changes state, as long as you've unmasked the pin. ChibiOS doesn't have an existing driver for the pin change interrupt, which we can totally implement ourselves, not a problem. We can get to that. But but I do have the standard interrupt lines, the isolated interrupt lines connected to the encoder inputs. Okay, so what we shall do to build our encoder driver is, just a little bit of brain fog. But or a little. It's late. I'm getting a little bit of a headache, but it's fine. Oh, okay, we're gonna see this. We're gonna try to run this before I go to bed. I want to see this attempt to run or not before I go to bed. I'm too tantalizingly close. Okay, so gotta build an encoder driver. Okay, so what we're gonna do is we're going to create a volatile. I think this encoder class I don't remember. Sorry, the encoder Arduino library. I can't remember. I think it might have been. I can't remember if it was int 32 or int 16. Counts pulses, releases 1.44. Oh no, I don't want the. There we go. GitHub repo. I want to delete that. Oh, trash. So encoder.h. Position, yeah, 32 state here. Cool, all right. So we got volatile int 32, encoder ticks equals 0. This read and reset thing, we'll do auto ticks equal encoder ticks equals 0 because it's read and reset. Alrighty, so we've done that, and now, actually, I mean, honestly, that should mean that we build. Obviously, it's not good because we still got things to do. But how are we using freaking half of the code? Okay. Either way, sorry. Not much data, thankfully, but lots of text, lots of binary. Okay. Not a problem. Okay. Stop saying that. Yeah. All right. So let's write a function. Void. Encoder ticks. I wonder, can you program bidirectional or both edges of... Let's see if we push 18 mega 328p datasheet. I can't remember if the interrupt pins on the Arduino are if they can be done, or I know obviously pin change can do whatever because it's just changed on it just detects that the pin's changed. But what I'm curious about is if the actual external interrupt pins can change. If you can use the standard interrupts as pin change interrupts as well. Any logical change on int1 or int0. Okay, cool. So we can actually configure the core interrupt pins as both. All right, so void IMU event. Not IMU, geez, encoder event. And the encoder inputs changed. Okay. All right, so let's figure out how to attach the actual... So while we're waiting on that, let's figure out how to attach the actual external interrupts to the Arduino through ChibiOS. I don't even know if that's implemented. Oh yeah, I think it is, but I can't quite recall. So we need to go to... I think it's called EXTV1. I think that's how the external interrupts work on Chibi for the AVR. So we need to go to how use ext. Is that even in here? That's not even in there. Okay, the ext driver is... How do I even enable MCU? Use int0 is true. Use int1 is true. Because yeah, they got these use PC int, but I don't, okay, so we've got this use PC int thing, but I don't think it actually is implemented anywhere. Because we see all this test code that, use pins, use this, but it never actually triggers any real logic. It's just a definition. Yeah, it's just definition not supported by... Yeah, okay. Yeah, clearly. Okay. It's not implemented. Okay, but either way. Hal use ext. So how do we in halconf? There should be an ext thing in here, but there's not. RG hal use ext. If hal use ext ChibiOS hal ports mega ext1 driver find string true. Use smart build. If not equal find string. Oh, it just forcibly includes it. Okay, cool. That works for me. But unfortunately, it doesn't make the it doesn't make IntelliSense happy. So anyway, I'll use ext. There we go. So we need how does this work? ext driver. Okay, so okay, so we need to go back into our ChibiOS docs here and close all this crap. Leave that. Leave Quadrature. Arduino, leave that. Delete that. Delete that. Move that over. ChibiOS. Alright. The ext driver is not even freaking documented here. Okay. ext LLD init. Where is that used? ext LLD init. It's only used in the AT Mega driver. Oh, would you look at that? That's brilliant. Okay. What does it even mean? Alright. So maybe we have to include. Oh, right. The ext driver is not really a thing. That I keep forgetting. Okay. So this is included. ext driver. So ext LLD init, that's called by no one. That is literally called by no one. Okay. So we have to call would have to call ext driver start ext driver are any of these defined? Okay, there is a HAL test that includes a demo, a thing here. Okay, cool. Let's look at the test. External callback, HAL toggle, syslock from ISR. Well, we're not in an ISR. Ext config. Yeah, HAL init, pad set mode, mode input, start, activate. Yeah, okay, cool. Channel enable, int4, ext config. Okay. Okay. So that's how that'll work. So ext start. Okay. So we got to do this manually. Okay. So attach encoder interrupts. Okay. So the callback is the ext driver x channel. That's static void. Thing. Channel make else did it know? Oh, I think VS Code died. Okay, fun. Okay. Bring VS Code back. Alright, ext. Make file. Well, it didn't. Not the make file. Sorry, halconf ext. Oh, no, it didn't implement it. Chconf. Nope, it didn't do it. Halconf. Main, nil. No. Main. Go to definition. Well, what? It's mad because it doesn't see the correct integer headers getting pulled in. Okay, well, anyway. This is making everything mad at me. Wow. Oh, what? Making everything mad at me. ext driver's undefined, but it is defined because all sorts of reasons. Okay, I hate this. Okay. ext driver, exp channel. Extern ext driver, struct ext driver, but ext state because it's undefined. We're just gonna to make this prettier. I hate this. It's not actually an error. Why does it not want? Why is this not real? Why is this blowing up? Who is including hal ext lld.h rg hal ext lld.h. .c. Form. Who is actually including this frickin' file? I am confused. Platform.make. Can you make the compiler include stuff? Yeah, I guess. I don't. If it compiles, I don't really care. Does it compile? No, it doesn't compile. Variable or encoder Static void. Because yeah, ext driver is not included. So something, okay, I'm missing something. This is the make file for test HAL. It's doing something that I'm not seeing. Pilers. Some make options it is passing that I'm not getting. Ooh. Is that why? No, that's not why. I'm getting that. Some configuration options that it's doing that I'm not getting. Use that. Use not that timer. US art. I squared Shay. Make file. Okay. Something is being passed in here that I'm not getting. So let me hack up my make file, or let me access my HAL conf here. ext. Why not? Enable the maybe that's a thing. Hold on. Nope, that wasn't it. Okay, what am I missing? I'm missing something. They're able, or maybe it's not working for them either. ext driver's undefined. I mean, here, what happens if I make clean? Hold on. I mean, it's going to fail. I mean, I just want to see if, just want to see if HAL ext is actually included in anything. HAL buffers, stuff. HAL board, boxes. Yeah, I didn't actually see HAL ext.c get included in any of this, actually. Never not make. So I modified their HAL conf ext on accident. Oops. I wanted to modify mine. Where's my CFG folder? HAL conf. Use ext subsystem. Maybe that'll quiet things down. No, it didn't. But it also pissed off a bunch of other stuff. Oh yeah, it even pissed off the LLD, unknown channel. This must be really dead. This must be a really dead subsystem. No, ChibiOS would be more equivalent to something like FreeRTOS. It's just it's basically a threading. I mean, it's a very small real-time operating system, and I hesitate to call it operating system because when you say operating system, you think like Linux or Windows or something like that. But realistically, it's a way of creating threads, or it lets you use a threaded programming model on a microcontroller. And the real-time part of it is a lot more complicated than I'm going to get into. But effectively going to give it a threading system. It's a threading system for a microcontroller. It's the best way of like making it. So if you ever use like P threads or C++ threads, like this is a way of getting that on a microcontroller. Just Chibi's really targeted for small platforms. Whereas ROS is a programming framework for robotics. It's less focused on so they operate at two different levels, really. ROS is a platform for writing services that talk to each other on top of and have data abstractions between each other, and then sharing those services. Whereas ChibiOS is really more of an this analogy sucks, but it would be easier to say that Linux and ChibiOS are more of the same level of abstraction than something like ROS and ChibiOS. Like, think about how ROS sits on top of Linux. I mean, it can sit on top of other things these days, but like ROS is a framework that sits on top of another operating system. You could say run ROS or micro ROS on top of ChibiOS. Actually, there are some examples of that running micro ROS on top of ChibiOS. ChibiOS provides the threading model, the multi-process model underneath, and then ROS would be a framework that would sit on top of that for writing services that communicate with each other. Actually, there are some examples in ChibiOS of writing micro ROS programs on top of Chibi, or replacing the micro ROS default, because I think micro ROS wants to use NutX by default, which is a bit heavy if you're running on a slower microcontroller. I mean, if you're running on something like a Cortex M7 or an M33, like, it's fine. But one of the slower microcontrollers is not really going to get. Maybe reboot VS Code and clear build. VS Pro has been known to get stuck on perceived syntax. Refuses to build despite clean code. Well, actually, I mean, this is me not using VS Code's build. This is me running make directly, and it's not happy with me anymore. What I think is actually happening is I think this ext driver that I've been checking out, I don't know if it actually works anymore. Because if I go in here so for one, I added something to a header to enable it that I couldn't find in any of the sample headers. And then the moment I start enabling it, the ChibiOS code itself starts complaining about things. And so I'm thinking this ext driver might actually just be dead or abandoned. So I'm actually going to give up on the ext driver, and we're just going to write our own. We're just going to start the interrupts directly ourselves. So I'm gonna get rid of this ext driver. I'm gonna close the ext driver thing that I've been looking at. We're gonna delete this hell use ext thing because it's causing problems. Close that. Encoder event. We'll just leave this as it were. Okay. So what I do need to look up though is how to wrap interrupts. Actually, I should probably just reopen the thing I just closed. Sorry. I need to remember how I'm supposed to wrap interrupts this, because you gotta have an entrance. They call it a prologue, epilogue. Okay, actually, yeah, here we go. So what we're gonna do is we're gonna define the encoder event as what it is. Static encoder event. They're going to say OSAL IRQ. Actually, do we just use the OSAL IRQ handler? Int 0vec. OSAL IRQ handler. Int 1 vector. So these are the actual. These functions are created in such a way that when the system interrupt or this processor interrupt happens, it immediately jumps to this function. So because we're now, have our operating system, a little one, an operating system running on top of us, we actually have to be, kind. So that's what these prologue and epilogue is. It makes sure to manage any ChibiOS structures or any OS structures that might otherwise get stomped on because of the interrupt. And so it's basically a hamburger around oh, oops, epilogue. All right, so we got that, and we're just going to call encoder event whenever this happens. So okay, cool. Okay. Actually, no. Realistically, if I'm going this far into this, I might as well just use the pin change interrupts. Realistically, but we're yeah. Fuck it. Whatever. Won't deal with that right now. All right. So now it's mad at me. What did I accidentally delete? Oh, right, because in hell. Alright, I define that as true. MCU conf. Okay. In this, we're gonna delete that because it's it's making our build really, really unhappy. There we go. Now everything's happy again. Okay. Attach encoder, setup encoder interrupts. This is going to be, let's see, back to the UTmega documentation. So we now need to set up external interrupt control register A. And then the mask. So flag register. We don't actually have to worry about the flag register. Okay. So we need to set up these bits to call the interrupt any logical change on interrupt. So that's set ISC11 to 0, ISC10 to 1. So that's 1 1 and 1 0. So we set 0 1. I'm presuming so 0 1 on the other one as well. So we need to set this 0 1 0 1. So what we can actually do here is we can say EICRA equals BV ISC10 ORD to BV ISC00. And this BV macro, it's just one shifted to the left by the bit. So it'd be like saying one left shifted by 2 for that ISC10, and then one shifted left by 0 for ISC00. Okay, so that turns on the interrupts, and then the mask, when this bit is set to 1, and the bit in the status register is set to 1, so if interrupts are overall enabled, the bit in the mask register is enabled, and the external pin interrupt is enabled, and you've configured the interrupt, then it'll trigger. So, okay, so EIMSK, external interrupt mask. We're going to enable int1, BV int1 and int0. So now our external interrupts are turned on those pins. And it will call this function whenever it'll call this function. It will call this function whenever it is doing. Okay, so we need to get we need to do a PAL or OSAL sys lock enter a critical zone from a thread. Oh, baby. OSAL sys unlock. Oh, right. From ISR. Lock from ISR. main function. PAL toggle. Where was test? Nah, I don't really care. From ISR. Where was yeah, there's that test HAL. What was it doing in here? Oh, sys lock from ISR. Oops. Sorry. Okay. Oh, unlock. Unlock from ISR. PAL toggle, PAL read, I want. What we need is auto bits equals PAL read port IO port 2. Alright, that'll give us the value of IO port 2. And because we're attached to, okay, sorry. And then bits equal, sorry. Let me say, sorry. We've got, what we actually want is the, we also want the encoder previous state, because we need to look for changes between the states. I mean, we know it's changed, but just in how it's changed is important. So we had that, yeah, encoder ticks. We also need volatile uint8 encoder state equals 0. And that's another thing we need to do. We need to define a function. Actually, maybe not define a function necessarily, but encoder state equals PAL read port IO port 2 shifted 2. Set up encoder interrupts and also get bits 2 and 3 into state bits 0 and 1. Basically what we're doing here is we're just trying to store the initial state of the encoder so we know what to check against moving into the future. So we got the encoder state. So encoder state is PAL read port IO port 2, 03. So that'll give us pins 2, because everything's starting at numbered starting at 0. So 0, 1, 2, 3. So the encoder is installed in IO port 2 and 3. And honestly, just to make things a little bit nicer, let's say port, or port line to port, right? Line, or PAL line, PAL port, encoder A line, shifted. Actually, no, sorry. Yeah. And shifted PAL port bit encoder channel A line. Yeah. Okay. So now we made it generic. So if I ever change channel A line, it's correct. It's sorry. Sorry. I'll read port. So yeah, that port shifted by PAL port bit. PAL port bit is IO port mask. Oh, sorry. PAL pad. Hold on. Read port. PAL port. Well, hopefully it optimizes that out. PAL line. PAL pad from encoder channel A line. Okay, well, you know what? Hopefully it can optimize that. We'll see what happens. Who knows? Who knows what it'll do though, you know? Encoder state. So we do that. We then say PAL read port, PAL port from encoder channel A line. Okay. And then we say bits is actually what we do is because it's bits 2 and 3. We would say PAL. We say bits equals bits. Let's see here. So we would say encoder state. Actually, here's the thing too. We need to. Oh, fun. Right, we need to fetch the encoder value atomically. Oh, that's going to be fun. Okay, ticks. They're going to say, how did I, Arduino, ChibiOS, atomic. Okay, sorry. Basically what we're trying to do, if we update the encoder value, it's, it can be big. Sorry. The encoder, yeah. Sorry. The encoder value is, we're doing is a 32-bit integer. Problem is that the Arduino, or the Uno, has an 8-bit CPU. So you can't actually update a 32-bit value in one clock cycle. So the problem is that if we start getting this operation to change the encoder value, we're now in a race condition because the interrupt can happen whenever. It happens whenever the hardware event happens. You will trigger the interrupt. And the last thing you want to be doing is being right here, reading the encoder ticks thing in the middle of an update, or setting it to 0 in the middle of an update. Like, that'd be bad. So I'm trying to figure out how to lock the. I need to do a lock. I'm thinking this lock thing is ch sys lock. Sys unlock, I think is what I need to do. Port lock enters a kernel lock state. Port lock. CLI. Clear interrupt. Okay. Oh, wow. Yay, the documentation. Is it safe to assume using lock? Okay, so doing that. You know, just to be a little kind, we'll move the state lock after we fetch the encoder ticks. Cool. All right. Nice. And technically the bumper's going to be the same way, but it is a single byte, so it can be updated atomically. But either way, we're doing our state thing. So what we're going to do is we're going to figure out all of our state transitions that are legal for quadrature encoder. So got this encoder state, and okay, so we're still in our interrupt. We're reading. Actually, you know what? We're just gonna syslock. No. What am I doing? Syslock, sysunlock. This whole thing is going to be. Okay, so we've read the bits. We've shifted the bits by 2. Honestly, encoder state is a uint 8. Bits, not that. So bits are shifted. What am I gonna do? All right, so we're gonna put the new bits in the last 2 bits. So, I mean, technically this could be optimized based on the way that I installed the encoder, but realistically, it might not work this way in real life, or generically. Pal pad, encoder, channel a line. Pad. And this whole thing is anded to 3. So what we're going to do is encoder state is equal to encoder state shifted left by 2. And we're going to anded to 0x, I think 0c. That'd be C is A is 10, B is, so that's 1100 is C. We can actually do 0, 1, 0, 0. No, you can actually do binary constants in C++. All right, and then we're going to AND that. So actually what we're going to do, sorry, we're going to say auto transitions equals encoder state left shifted 2 ORD 2 bits, and then encoder state equals bits. So, sorry, yeah. So what we're going to do is holding this as const. I'll do the same function that I wrote down there. Encoder state equals yes. Transitions is encoder state left shift to 2. Okay, so get the encoder transition map. Okay, now we're going to figure out what to do. Of course. Switch encoder state. So realistically, the only valid state transitions are one where a single bit changed. So we're going to do a bunch of case state. We're going to do 16 case statements for all 16 combinations of 4 bits. So if our state is 0, 0, 0, 0, actually 0b. So basically all of our initial states here are the states where nothing changed. The old bits is equal to the new bits. But that doesn't make any sense to have happened because the interrupt should only be called if a state change happened, but just in case, 0, 1, 0, 1, case 0b, 1, 0, 1, 0, and then case 0b, 1, 1, 1, 1. So we're just going to break in all of these cases. Because nothing actually changed. The upper and lower bit pairs are the same. Nothing changed. Figure out. Okay, so, and then the next, so the first case will be 0, 0, 0, 1. So the previous state was all zeros, and now, so the way that we're labeling this is that channel A is the lower bit, channel B is the upper bit, and then the previous state of channel A is the third bit, and the previous state of channel B is the fourth bit. So, so we went from 0, 0, so both zeros, to 1, 0. So we're going to call that an increase by 1. So we're going to say encoder state, encoder ticks, plus plus, break. And then we're going to say case 0b, 0, 0, 1, 0. So now we went from all zeros to channel B being 1. So basically you'd say all zeros. Now channel B is 1. So we're going backwards. So we go encoder ticks minus minus. Break. And the next case is 0b, 0, 0, 1, 1. Which this is illegal. This can't... Something happened because we basically went from none of them are set all the way to both of them are set. We skipped a step, so something went wrong. So we're going to say this is double transition. Double step, which is bad. All right. So now we're going to analyze, case 0b, 0, 1, 0, 0. So we went from basically one being set and the other being 0, transitioning to 0. So this is us going backwards because channel A went from 1, 0 to 0, 0. So we went backwards. So this is encoder ticks minus minus. Break. And obviously our no change case was here. And then case 0b, 0, 1, 1, 0. So again, this is both bits change. This is a double step. This is our bad double step case. Double step. Bad. Okay. Case 0b, 0, 1, 1, 1. So we went from 0, 1. So, so 0, so basically 0, 1, this state, went from that to 1, 1. So we actually went backwards. Again, wait, hold on, I did this wrong. 0, 1, previous state. So 0, 1, and then we went to 0, 0. Oh, no, I'm sorry. I counted this wrong. So we were in... So sorry, for this first condition here, 0, 1, 0, 0. We actually... Sorry, I did this wrong. So 0, 1, 0, 0. So let's see, we were in... This, so basically that's this state. We're... no, wait. Hold on. I think I did double bad. Sorry. Okay. Previous state was B is 0. So B is 0. And then A is 1. And we went to 0, 0. So yeah, that's backwards. So, sorry. Our 0, 1, 1, 1. So we're in A is 0. B is 1. No, I got them backward again. I got them backward again. Sorry. A is 1, B is 0. So yeah, A is 1, B is 0. A is 1, B is 0. And we go to both of them are true. So that is our move forward case. So that's encoder ticks ++. Okay, so now, so that's the other state. So case 0B, 1, 1, 0, 0. So again, this is a double step because 2 bits change state, so that's bad. So that's going to be break. Should probably keep an error counter. 0B, 1, 1, 0, 1. So that went from both bits are 1, to only A being true. Because it went from both bits are 1 to B is 0, A is 1. So yeah, it went backwards. So this is our encoder ticks minus. This is our minus case. Break. Notice that for every one of these 4 state groups, one is a double step, which is bad. One is a no change, and then one is a singular. One is a step in either direction. So then we got case 0B 1 1 1 0. So we went from both being 1 to only B being true. So that's A transitioned to 0. So that's our forward case. So that's encoder ticks ++. Then we got our 1 0 1 0. Wait, I bungled. Wait, what? Hold up. Sorry. I missed one. I missed our 1 0 case. Okay, sorry. All right, final case. So yeah, so we got 1 1 to 1 0 to 0 0, double step that's bad. We did these ones. 1 1 1 1, no step. So, case 0B 1 0 0 0 is going to be, so we went from B is 1. Sorry, so B is 1, A is 0. So B is 1, A is 0. And we went to 0 0. So that's our forward stepping case in this. That's our forward step case. Because we went from 1 0 to 0 0. So that's our forward case. And then case 0B 1 0 0 1. That's our double step, which is bad. Break. We got our no change, our 1 0 1 0. Got our case OB 1 1 0 1 1. And that's, we went from B is 1, A is 0, back to both are true. So this is our reverse step. Encoder ticks minus. Break. Okay, cool. So we've got our whole state map done, all 16 cases. So let's actually just make these a little nicer to deal with. So we're going to copy, because we're going to take advantage of a fall through on case statements. So we're going to cut all of these no changes to be right next to each other. 0 0 1. There's 1 0. So yeah. So take advantage of our fall through 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. All right, cool. So now let's cut all of our double steppers together, I guess. So that's a double step bed. That's the 0 case. Where's the 0, 1 double step? There's the 1, 0 double step. And the 1, 1 double step. All right. And so now we're going to cut all of our plus cases together. So where's the next plus case? Is here. Next plus case is here. The next one is here. Just and the rest of them are all our fall throughs. Okay. No change. Double step. All right, so we got our switch encoder state. All right, so we got our encoder tick counter now. So that, all right, it built. Who wants to run it on the robot? Let's see if this works. I mean, we do also, theoretically, the last thing we could do just to make full full compliance with the original system could be her bumper contacts. Oh man, you know what? It's already late o'clock. Let's try it. So we got where's the pin change interrupt system? PICR, yeah. Yeah, pin change interrupts are okay. So those int 0, int 1 pins that we were looking at, those. Sorry, the whole point of those is to the discrete event triggers a discrete interrupt. That one pin will trigger that one interrupt. Pin change interrupts are, and those other ones you can say only rising edges would trigger interrupts, only falling edges, or the pin being 1 or being 0 could trigger an interrupt. Then level triggered versus edge triggered. And I mean, we're trying to use both edge triggered. So I mean, we could, whereas pin change interrupt is always double edge triggered. Sorry. Pin change interrupt is always double edge triggered. And it doesn't support level, it's only on level transitions. So the pin changed. And you only get one interrupt for the whole port. So if any pin that is unmasked on that IO port changes, you'll get the interrupt. Which, depending on what you're doing, could be completely fine. They're just less granular. So you need a lot. There's a little. If you have multiple things attached to pin change interrupts, there's a little bit more latency because the CPU has to figure out which thing changed. So what we'll do. So we're gonna go back to our Uno schematic, and the bumper is on. Okay, well the bumper's on IO port 2, so we can use pin change 2 because that's. Pin change register 2 because that's, well, actually, I mean, which pin change interrupts are which pin configurations? Port D is pin change 16 through 23. Okay, so it's the upper 8 of them. So, pin change interrupts. So, Yeah, so 16 through 23. So PC ICR bit 2, pin change interrupt, and we're going to want PC mask 2 to set which ones we're interested in. So, all right. So let's do this. Yeah, why not? Okay, so OSAL, IRQ, handler, PC int, 2 vector, OSAL IRQ prologue, OSAL IRQ epilogue. I'm gonna say bumper contact. Yeah, I set it to true. Because that's a single byte on AVR, we can actually set that just fine. Bumper contact. All right. Do I have to read the pin change mask register? I probably do. Or the pin change mask register. PCIF. I don't actually think there's a register to check which... Yeah, it's an OR gate. Yeah, you don't actually know which pin changed. That's the other thing, is you have to do the state check. You need to store the previous state of the port, just so you know which bits changed. So what we're going to do is... bumper A, bumper B. Alright, so I'm going to say bumper contact. Shit. Bumper contact to do. Detect IMU interrupt as well. And we're going to come down here and we're going to say, so rather than all these attach things, set up bumper interrupts. Get bits. Oh wait, that's not the same thing. Set up bumper, and I did the same thing. Encoder state is these two shifted down to the first bits and into 3. Do the same thing up here. Bits shifted down, and encoder state is left shifted or to bits. Okay, cool. We're good. Technically that's excessive, but whatever. The fun optimization will only apply. Alright. Alright, so PCMSK2 equals... Okay, and the funny thing is that the mask bit is technically setting the bit, unmasks it. It's the mask register, but the mask register defaults to 0, which is everything masked. If you set the mask bit to 1, it's unmasked. Yes. Okay. PC mask 2 equals pal read. No, what am I doing? Pal pad encoder. Oh, bumper A line. Or to BV. Pal pad bumper B line. Okay, and then we do PCMSK2 is set to that. And then we do PCICR equals BV PCICE2 PCIe2. Not PCIe, not PCI Express. And then just pin change interrupt enable 2. 18 is executed. Okay, PCICR, and then do I have to EIMSK ECICRA? I don't have to set any other registers to interrupt. Nope, looks like that. Okay. In theory, we have made a functionally identical sketch. only took 4 hours. Maybe it'll work. Maybe it won't. But let's see. Do we have a hex file? We, in fact, do. We're going to copy build / motion controller to the robot. Kybernetes local. Oh, sorry. Oops. Dot local. Okay. Let's point the robot at the cone and see what it does. Oh boy. All right. We're getting ready. So I got my radio kill switch. I'm not steering it. I'm pulling the trigger makes it go. Pulling the trigger enables the motors. So we're going. You know what? Yeah. I'm gonna set up the camera. Here, hold on. Let me. We've woken it up. Not flashlight. Undark mode. Hold on. And droid cam. Alright. So here, I need to finish flashing the. Where? Yeah. So we're gonna sh. No, we're gonna mosh. Kybernetes.local. I don't have another one of these hidden somewhere, right? No. Alright. We're going to say. Alright, we have our motion controller sketch, so do we have AVR dude installed? We do. What happens if I do a make program on this? It's gonna flash to this Arduino Uno sitting on my desk. I just wanted to get the command. Well, I got that motion controller code sitting on that Arduino. Okay, so this is what it's gonna be. This is our flash command, more or less, except I have a ls dev motion controller port that I have the serial number. There's a UDEV rule that reads that if the serial number for the Uno that represents the motion controller pops up, it links it to dev motion controller so that I can have a device node connected to the Arduino I know is my motion controller. And if anybody's curious about how that works, rules.d, Kybernetes.rules, we've got if the serial number of that specific Arduino that's in my robot is found, it then symlinks it to dev motion controller. So we can do this. We got build motion controller dot. No, we don't have a build motion controller dot hex. Sorry. Write flash. Just have to do flash w motion controller dot hex, right? Okay. D u flash. Alright, 115. Oh boy, motion controller. We are flashing. We are oh boy, it's the sketch is loaded into the Tmux. Right. Okay. So the sketch is the hex file is flashed to the Arduino. Let's see if it works. Okay. So we got to go to programs. Kybernetes Python. We gotta source our depth. Source our Python environment that all of the shit to make this robot work is installed in. We're gonna try the find cone program. Shit. Okay. During the handling, canceled error on wait for data read exactly. Aww. Aw, it's not working. It's not working, guys. Ah. Wait for self-reader, timeout 5 seconds, and motion controller.py. Oh well. Okay. Not the climax I was hoping for. It would have been hilarious if it worked the first time. Okay, so what did we do wrong? Oh, God, it's so late. But what did we do wrong? That is the question. So realistically, we need to. Oh, how do you even debug this? Okay. Well, shoot. Packet thread, main thread. Did I do anything immediately particularly stupid? That's the question. Is the speed of the serial port right? Is the other stuff right? So channel, close this stuff, close that, close that, close that, close that. Actually, won't want those last two. But HAL config, we want the I2C controller, MCU, we want that shit. True. All right. One question is whether the timer v1 is usable. But gbconf HAL. Default serial bitrate. Default serial bitrate. Well, hi. It would be nice to know where. Where I broke it. That would be nice to know. I mean, here, hold on. Kybernetes, motion controller.py. Yeah, it's expecting 250 kbaud. Okay. But what does work? Let's see. Does anything work? Another thing that might just be wrong is I might not be given these enough stack. That might, I mean, that's always something to try real fast. You never know. These 256 bytes. We'll set this to 1, just because that's what we had previously. Yeah, so start serial, enter packet loop. Well, sending the sync packet from here would be bad anyway, because that's supposed to come out of the packet loop. None of this code should actually be, that should really be sitting on the serial port. Oh, that's a good point. Oh. Yeah, what happens if we try to write to the serial port before it comes up? That's a good question. So how about what we do is, no, we don't have to worry about that. Packet loop, while one packet loop, break. Hopefully I didn't call return here. Actually, no, return's fine. Return's fine because packet loop is called in this loop. Yeah. So yeah, I can return from this function safely. Controller update, sleep milliseconds. That's fine. That's in loop. Okay. Well, let's remake that. reflash that. Okay. Safe mode fuse is okay. Oh, actually, is there any data at all coming from? So STTY. Man, STTY. So if we set the speed of this baud rate, deviations, God, what if we do something evil, like ch thread sleep, thread wait. What if we did that? What if we made it? What if we made the core loop wait a second before, after we start up the serial port? That's evil. I shouldn't be doing that, but whatever, man. All right. We need better synchronization than that, but whatever. So how do we... Can't determine... File... Oh, oops. Maybe Arduino. Alright, yeah. Alright, so what does Kybernetes... controller... Yeah, so if we try find cone now, it's probably gonna die. But where did it actually explode? It exploded in line 518, then 327 in synchronize. So it failed. It failed to even synchronize. It failed to read, which means the Chibi wasn't even transmitting. I'm really curious what happens if I, I mean, there's status thread, right? So, what happens if I, yeah, so so man STTY, so baud rate, baud, special settings, and what happens if I just minicom? Do I have minicom, picocom? Yeah, let's see what happens if I just, it's gonna be all bad. But nice. So there's just nothing coming out of it. Well, that's not good. LED. Yeah, what else do I do a make program? I'll do that on this side. I got an Arduino Uno plugged into my desk. Or into my computer on the desk, so the LED turns on. When do I turn on the LED in... Okay, what happens if I picocom on my local machine? Picocom... Yeah, it's not exactly flashing its transmitting lights. Yeah, it's not happy. So, Yeah, JVM for microcontrollers has existed. If you also want like another, well, actually, you want like probably one of the most cursed things that I have. Well, I don't want to call it cursed because I dearly loved it, but one of my first, I used to call them real programming languages. I like back when I first started when I was a kid, I was playing around with Lego Mindstorms and it had like a block based, this block based programming environment, and it was based on LabVIEW. And I remember it's like writing programs as code was like real programming, right? And so if it's called Lehos, I think, but yeah, Lego, yeah, the Lehos Java for Lego Mindstorms, and the first Lego Mindstorms computer, the RCX, it was an 8-bit Rensys H8300 processor with like 32K of RAM or something, and you could write Java programs that would run in it based on I think the whole thing was based on J2EE or some Lego micro nano VM type thing, and I mean the 32K, but it still had the full threading library. So like while it's like, oh my god, Java on a microcontroller, it was like it had threads. Like it is hilariously powerful. I mean just functional for what the horribly tiny footprint it was in. Oh yeah, the Tiny VM project. When was this last updated? Like 2000? Yeah, Tiny VM took 10K. Java in 10K. Like, yeah, it's just funny. Either way, okay, so what the hell is up with me robot? What did I do? I tried to do a lot of things at the same time and it's not working. So, man, okay, so realistically, the place to start would be, fixing now that I've completely disabled my robot on accident. Not on accident. We tried changing things. What if I gave it even more stack? I doubt that's gonna fix it. But who the hell knows? Make data. Oh, I've got the oh. Yeah, it's not happy with me. Okay, so it turns on the onboard LED, which I don't know what the heck I programmed the onboard LED to do. Uno. All of these are that. 1, 2, 3, 4, 5, 6. Onboard LED is pin 13, right? Well, I mean, it's not pin 13. It's something. SCK. Or the green on. Okay, green on. No. Where is the? Wait, yellow LED. Yeah, it is the SCK signal. Okay. So that's on port B. Oh. Okay. Maybe that priority thing was bad. Maybe I'm stomping. Who knows? That's what's wrong. I highly doubt it, but We're trying anything at this point. You know, honestly, we're just gonna hack these. We could just hack this up just to make sure that it's actually booting correctly. We just say we can keep that in a sleep loop. We're gonna say ch print. Oh, it's the hello world again. CH Chanwright hello world. There's like a channel printf function, but we're gonna call this okay. Just to make sure that the thing has come up, we're gonna I'm gonna do this. All right, so that should give us cat of tty. Oh, okay, yeah. Minicom, ecocom. Wow, it's not sending anything. What? Is the baud rate wrong? Hold on. Oh, it's sending stuff. Oh, it's sending hello world. Cool. And then it freezes. I shouldn't be doing that. I mean, realistically, I've commented out everything that isn't. I don't even call loop anymore, so I don't. So realistically, something I broke something, but I don't know what. Okay, you know what? We're gonna comment out, just comment out stuff. Yeah, we're gonna comment out this steering stuff, and then we're gonna rebuild this. We're gonna. Did I already make program make? Part of me wonders whether I stomped on something important in the hello world, hello world, hello world. Oh! Well, now it's running. And what I changed here was I changed the timer I changed my usage of timer 1. When now it is printing hello world. And if I re-enable all of this timer 1 stuff, I bet it'll die again. I bet it's using timer 1 for the RTOS timer. Oops, hold on. I didn't make program. Yeah, it's dead. Okay. It's dead. Okay. It's using timer 1 for the RTOS's tick. Okay, so its clock is provided by timer 1, which is also what I attach the servos to. So I have to figure out how to change from timer 1 to have the RTOS chain not use timer 1. So cool. So we have a loose idea of what I did wrong. I mean, we have a good idea what I did wrong. just comment out these 3 lines and then it starts working again, which is pretty clear to me what went wrong. Or pretty clear to me that my manipulation of timer 1 is what's breaking things. So ChibiOS, how do we not use timer 1? So there must be something in this HAL configuration. Hopefully there's something in HAL configuration or MCU configuration that says which timers, maybe if we tell it that we're going to use PWM on timer 1, maybe it won't use timer 1 as its for its clock. So we're actually going to look for PWM use timer 1 in Chibi here and see what that actually, if that triggers anything. Or triggers anything in the kernel side of things, maybe. AVR timers. Yeah, let's see what see if this changes anything. AVR timers.h. HAL LLD. Ooh, yes. Timer 1 cannot be simultaneously used by multiple drivers. OSAL mode. Timer 1 cannot be used by drivers when running in tickless mode. But I am not running in tickless mode. I am... Timer 1 cannot be used by drivers when running in tickless mode. Okay, that's fine. I don't care to use general purpose timer. Okay, well, let's see what happens. Make program. And picocom. Hello world. Still dead though. So it's something not right. What if maybe there's something else happening. What if rather than hacking up those registers, if there's something special that I need to do, MCU configuration. Yeah, I want to use PWM use timer 1. So let's look at the PWM driver, because maybe my override. Why is it using timer 1 over timer 0? So I don't actually know if it's using. Okay, well, sorry. So I'm using timer 1 for servo control because timer 1. So on an Arduino Uno, there are 3 timers. There's 0, 1, and 2. Timers 0 and 2 are 8-bit timers. Timer 16 is a 16-bit timer. So one of the cool things about timer 1 in the AVR is that timer 1 has the ability of setting the upper bound of the PWM clock. Okay, so the way that PWM works, I mean, there's actually, I might as well, I'm going to try to explain it like verbally, but there's a really good graphic in the documentation. So this is called fast PWM. So basically what happens is for PWM, the timer is counting constantly, and then when it hits the maximum value, it rolls over. And so the idea is typically that when the timer hits 0, it overflows. It sets the pin to 1. It sets the output pin to 1, and then there's a register that you set a value to, and then whenever the timer hits the value of that register, it turns the pin back off. And so you vary that register between 0 and the maximum count of the timer to control how much of the timer's interval the pin is on for. And so with servo, so I'm using it for servo control, and servos need a 50, well, old servos needed a 50 hertz update period, but digital servos can handle usually up to like 400 hertz input signals. But so basically that's what that FCPU thing was, ICR1, this thing was, is that I decided to use a 333 hertz update rate for my steering servos, and while all the timers in the Arduino are capable of PWM, only timer 1 has this ICR register. And typically it's used as what's called the input capture register. That's what it's called, ICR. But without getting into what ICR, what that input capture thingy actually is, you can, in PWM mode, you can use that register to actually arbitrarily set the top end of the timer. So what I've done is I've set the upper bound of the timer so that it overflows at exactly 333 times per second. Just to give me more control over the timer's period. And so I want to use timer 1. That's why I'm using timer 1. But I don't know if it's using... but clearly something is using timer 1, or something's happening. And that could be something as simple as... it could even be something as simple as... maybe it's not using timer 1, for timing. It could be trying to set up an interrupt or something for timer 1, and I'm not initializing the interrupt and something bad's happening. I don't know. It's just a theory. But yeah, so if I comment out the stuff that I did, it starts saying hello world just fine again. Okay. So yeah, clearly something. Okay, so let's see. So ChibiOS does have a PWM driver. Oops. So let's see if we can use... Let's see if using the PWM driver unbreaks what is happening to me here. Well, maybe... So we got... Yeah, because there's this periodic notification. I'm kind of curious if what's happening is it defines a handler for like overflow interrupts for like timer 1, and because I'm just manually manipulating the registers, like the handlers aren't set correctly because I'm just manually manipulating registers and I don't know what Chibi's doing. So I'm going to use the PWM. Let's see if I can use the PWM driver instead. So PWM enable channel. So PWM driver. So let's try. So yeah, halconf PWM true. And maybe we can set PWM enable channel. And I'm kind of curious. Yeah, what's the implementation on the AVR side though of what the PWM driver looks like? Oh God, please tell me they have the PWM driver. Oh, thank God. Okay. Here. Well, we want it to use AVR PWM use. We're going to go add this to our CPP. Oh, well, that made it mad. Yeah, did I accidentally like enable the interrupt or something? Yeah. Melody init channels. Melody start. Otherwise breaks table ICR equals period. Okay, yeah, PWM enable channel. Okay. So yeah, let's try this. PWM change period. period. Yeah, F CPU divided by 333 minus 1. Minus 1. Enable channel. Enables a channel. 0. PWM pulse was numbers. Alright, we're going to say 0 for now. PWM enable channel. PWM D1. 1, 0. Maybe if it was setting OCR1A. Yeah, so maybe I can say PWM. How do I actually set the channel? Change period, maybe? PWM change period. No, that's with the driver. PWM init, PWM change period. Wait, do I? All right, hold on. Do I need to enable channel, enable periodic notification, start? Oh. Do I have to say PWM enable channel every freaking time I want to change the period? That's interesting. Interesting. I don't know if that's right, but means we can delete those two because we're calling set throttle. PWM start. Let me see if there's an example. RG PWM. There's a test how. I'm looking for test how. Yeah, here we go. PWM3 config. PWM frequency. PWM period. Channel 1 activated. What is the PWM period? Was I turning on the was I turning on any of the prescalers? Was that just enabling? Hold on. What was I doing here? Timer counter prescalers. CS10 with none of the other sets. CS10, no prescaling. Cool. Cool. All right. So. Oh, no. So yeah, we're just copying the just copying this. Yeah, oh hey. Okay, so we're setting that up, setting that. I think that'll work, right? make timer 1 cannot be used by drivers when running in tickless mode. That's why it was breaking. It's because timer 1 is being run in tickless mode. And so I need to not run in tickless mode. So tickless. Why is it running in tickless mode? Who enabled tickless mode? When did I enable tickless mode? Okay. Is nil always in tickless mode? That would suck. Okay, hold on. Why is it in tickless mode? Wait. How do we enable tickless mode? Wait, how do we enable tick mode? Ticked mode. Huh? Okay, hold up. System tick frequency, tick resolution, time delta constant. If this uses the classic periodic tick, so it is the minimum number of ticks that is safe to specify in a timeout directive. Huh. Medium HAL LOD, vector 11. Ah, it's really mad at me. Vector 11. Oh. I didn't override vector 11. Did I? Ooh. Number 1 comp a vector. ST mode, systic mode. This was 2. I needed a rebuild. Okay. Halconf, chconf. Hold on. Okay, make program. Okay. Let's see. Can I get my picocom? Oh, looks like I'm transmitting. Alrighty, I'm transmitting. Hell yes. Okay. 4, 5. Okay. Sweet. Okay, so I'm transmitting now. So let's re-enable all the stuff that we disabled. And I do want to the slow level driver thingy here. PWM enable channel. We really have to frickin' deal with to override this every time I want to change the OCR register. There's got to be a quicker way of doing that. Doesn't look like it though. Doesn't look like it really gives me away. I mean, I could just set the register. Like I know how that works, but we're doing it the chibi way. We're doing it the chibi way. So we're doing. Well, anywho, let's re-enable what we actually would like to work on. With, I mean, let's re-enable the actual like core logic. Loop. Comment that out. Make clean. Sorry. So if I make program, I should just see my. If I try to connect to it, I should just get junk flying out of the. Well, I don't want to say that too much, but. Yeah, I should just see stuff. Yeah, it sends stuff. But then obviously, like, it can't get I2C data from the radio controller because the radio controller did that. The hardware isn't present on this thing. So, okay. It's doing something. So we're gonna copy that over to the robot. We're gonna not use the right terminal. Okay, moment of truth. Round 2. We're going to flash the code to the robot and pray that it works. Alright, so we have flashed the Arduino. And we're going to say find... Oh, Jesus. Alright. Well, that's a different error. Oh, no. Oh, God. Expected a bytes like object string found. Oh no, did I forget to... Uh-oh, wait. I didn't write it. I didn't keep writing hello world to it, right? Okay, I mean, it is sending all sorts of data. That's cool. But it's still got something slightly wrong. Find cone. Or maybe it wasn't quite wrong. Oh, no, it's dead. Okay. All right. Obviously, something's wrong. Okay. Clearly, data join, serial async IO, expected a bytes like object string found. But that's okay. Hold on. Maybe that's just me. Maybe that's just me not code. Did I change something and not update it? Hold on. I don't think so. Yeah. Oh, right. The IMU system's not turned on. Let's see. Nope. Never reported. Let's see, remote control. Just trying some of my different little test programs, seeing if any of it works. Nope. Okay, so, well, at least the controller is up now. It's just not communicating correctly. Handling log lines. Yeah, what the hell? Yeah, just for giggles. Not for giggles. Sorry. We need to. Yeah, did we remade this, right? Yeah. All right. So what? I mean, we changed a lot of stuff. So what did I do wrong? It is a good question. Oh, it's been 5 hours now. Okay. Alrighty. Let's see. Roller update. Send in stuff. I should send in junk. I mean, the data's coming over because you can, as I'm rotating the wheel, I can see a couple of the bytes around like this location here changing. Like for instance, this one you can see change too. If I pull the trigger, if it's 4, 5, 6, 7. So I mean, clearly I2C bit's working because otherwise it wouldn't be sending data like this. So a few pieces are working. But clearly not completely, which means I probably have like an off by 1 problem in some of these response type systems. Yeah. Like maybe I did not buy 1 here, like Chan available for write less than or equal to 2, or receive transport size plus 2. How to write the type. The type is still receive type, so instead of writing, I got write 1 byte type. Chan write that. Also, that's a question. What is channel write actually doing? Does channel write, does it actually just call loosely into, doesn't stream write, sequential write, function writes a buffer to stream. It's not like padding or doing any other kind of stuff, right? End of file condition. Enter to buffer max amount of data to be transferred. Here's also the thing, like, who knows if, we don't even know if we're getting this return false, like, being called. Maybe I did the checksum wrong. No, I did the checksum right. All right. So some things are clearly working, but others aren't. I kind of wonder if this sync packet. I wonder if the packet loop is even send sync packet loop. Blocking read. I mean, this should be 1, right? Yeah. Not equal packet type. Something went wrong. Like, for instance, what if I didn't call send status packet? What if I never sent a status update? Will I ever actually reply? Yeah, like, for all I know, my handle thing isn't even ever running. Obviously, like, something's working because the serial driver starts, but packet loop, go to definition. Okay, well, I mean, I've installed it, so let's try. I mean, it's not going to work because yeah, but like if I try to do like find cone, hopefully, like it should time out or something. Yeah, wait for timeout. Chan read. I wonder if it just like where's motion controller? Init. Yeah, because like default baud rate, synchronize. Sync packet is exactly 16 FF, so find the remaining 15. And the first sync byte. Connection. Start. Yeah, synchronize. So I don't know if I ever actually send the sync request here. So reader writer start. Yeah, it looks like okay, I mean, I'm transmitting something, but like, for some reason, looks like I never send this early sync packet. Sync. Size of packet. Yeah. All right, SD1. It never synchronizes. Yeah, maybe there's a difference between maybe the ChibiOS, because I mean, yeah, well, I thought Arduinos basically they always reset when you opened their also they basically reset whenever you'd open their serial connections, but maybe that's an Arduino sketch thing. I doubt it. Well, let's see. Well, let's do a little bit of hacking on this. So I'm gonna say await async IO sleep 1. I think that's async IO Python. Okay, yeah, that's what I thought. Async IO.sleep 1. I'm gonna say self await self dot send packet, send type. Oh, is the sync packet 15 bytes and not... Oh, crap. Okay, Hold up. I mean, it should send... Hold up. What did I make it do? Hold on. Channel write, channel do the thing, channel handle sync packet. Send sync packet. No, don't. Give me, what did I change? 0 to 16, write, sync. Oh, no, okay, we're good. Oh, right. It's... Right, the sync packet is type sync with 15 subsequent sync bytes. Okay, right, okay, because the way that I implemented packet transmission. Okay. Okay, that's right. Wait, self.send packet. um I mean, why? All right, undid my change. But why wouldn't it? Why would transmit over there work, but not over here? Send sync packet. All right. Simple printf debugging. You know what might be happening here is I think the Arduino serial.begin waits for a connection. I don't remember. I have this feeling that AVR serial.begin. Oh no, okay. In such cases, some serial port. Okay, never mind. Okay, so what's happening? Alright, hold on. Else. I mean, it's a non-displayable character, so I mean, it should have worked. Hello. work. Okay, make... We're just doing printf debugging. We're just doing printf debugging. Hiko.com. Oh, no, it's working. Okay, it just doesn't do that again. Okay, that's fine. Okay. Hey, it came up. Obviously, that's not doing a thing, but let me make sure that a status packet sends. Let me uncomment out my commenting out. God, it's midnight. Send the packet. All right, make... maybe this will work. Well, cone contact. That's not right. The bumpers is not how they work. Something's funky. But hey, the bumper, it reported bumpers pressed for some reason. Okay. That's probably going to time out again on trying to open the thing, because the reset thing that the original... Yeah. Huh. Interesting. Okay, It looks like I need to make sure that the code on the robot intentionally sends the signal, the synchronization signal, because, I'm going to say await self dot, or async IO dot sleep to sleep 1. I mean, it only takes so long to come up. Oops. Let's say synchronize. We're going to say wait for send a sync packet. We're going to say say packet equals sync packet okay. self.send packet, sync packet, actually. Async IO is not defined. Interesting. Huh. Okay, well, if we send the sync packet, it should always start the thing up, because it looks like, unlike other stuff, let's see, it should, yeah, there we go. Now we're actually, so one of the interesting things with the Arduino is that with the previous Arduino sketch, it always looked like, if I move the robot, the fix should change, right? Yeah, because I'm moving it in the field of view. Okay, that error number is the camera reporting the steering error just sitting around the cone. But okay, so one thing I used to notice with Arduino sketch, or using an Arduino sketch versus this ChibiOS thing, is that every time you open the serial port, the Arduino would reset. And I don't know if that was, I don't know where in the Arduino that is. Like, clearly it's something it's integrated into the sketch and not the bootloader of the, or the board in some other way. So we have to I was getting away with before that every time I'd open the port, the Arduino would reset. So I'd always see that sync packet, and I never actually specifically requested it. So that was actually technically a bug in my code for the last number of years. Other than that, all right. So yeah, wait for the Uno to boot, send a sync packet. We're now synchronizing all the time, which is good. So we tell it to move. And then when I pull the trigger on the controller, it immediately transitions to cone contact, which is kind of funny. So what we're going to do in this, in our find cone program here, we're going to, I always forget to not, wait for idle, s set pid moving, while true, configuration, get status. We're going to just print out the controller status. Print status equals S. Just for some debugging sake. Yeah. I guess I'm not throwing status unless emotion, all of our stuff, state 32, armable, bumper pressed 1. Why is bumper pressed? Pressed 0. Bumper pressed is PAL read line A. Line B, or bumper contacted. True. Oh. But I mean, that really shouldn't make a difference. Right? All right, hold on. I should get status packets even when I'm not armed. Yeah, because I'm always, while true, please arm controller to continue. Oh, that's probably what's going on there. I am getting status packets. I'm just like minicom, sorry, picocom. Yeah, I'm getting status packets. Sorry, it's fine. But why? Why is bumper pressed? And it's pull up. So if the bumper's not I mean, it could also be that, like, Actually, you know what? I mean, we can always just step through this manually. Were these knots? Digital read, bumper P pin, A pin, PAL read line, A pin, B pin. Get these backwards. Bumper A line 4, 5. IO port 2. And I do pull ups. So local state is crawling forward and the bumper is pressed. Which means that ALN pad set line mode, pull up. Huh. Why is the... just for shits and giggles, we're going to say bumper press is always false. Never contact 0. And then flash that to the controller just to see. CP, copy that over. Flash that. I just want to see the motors come up. It's all I want to do. I just want to see the motors engage. And it's not moving. Throttle input, target 50, output 350. Enabled as 1, bumper press 0. It's not running. Wonder if that's just because I didn't set the outputs. That's probably because I didn't set the outputs. I think, oops. I don't think I set the outputs. Okay, fine. Let's do it in the ChibiOS way. Yeah. Servo pin 9 is port B. 9 and 10. And we got port B1, port B2, right? And is that the pins from the port B, port B1, port B2. Yeah, all right. Fine. Servo throttle line as PAL line IO port 1 pin 1. Oh, pin 2. Fine. Servo steering line as PAL line IO port 1 pin 1. The steering pin was 9 on the Arduino. That's port B1, IO port 1, 1, then port 10, which is the throttle, is port B2. So that's pin 2. Perfect. Okay. I'm going to come down here. We're going to PAL set line mode servo, steering line, PAL mode, output push pull, PAL set line mode, servo throttle line, PAL mode output push pull. That accident put semicolons on those damn things again? Nope. Alright, I have port 1. I have port 3. This was PB. I don't know. Yeah, watch me actually have gotten these IO ports completely freaking wrong. IO port 2 is... Oh yeah, look at me. I got PD. Oh yeah, that's why the bumpers aren't working. I got the IO ports completely freaking wrong. And yeah, Danish, you're right, it is midnight. I'm so tantalizingly close. Okay, so IO port 2 is port B. IO port 3 is port C. IO port D is IO port 4. All right, I completely got all of these wrong. So this is 4, 4, 4, 4, 4, 4. And this is 2. Where's IO port 2? IO port 4. I didn't put them anywhere else, right? Okay, sick. So all of that should work now. I mean, hypothetically. Oh, hey, SCP. Kybernetes.local. And let's uncomment those the poor bumper hack, poor hack job I did to the bumper code. Yeah, here we go. Alrighty. So we've done that. Copy that over to the robot. Flash that. Hopefully this works. Hopefully. Hopefully. All right, find cone, moment of truth, spinning up. I hear the robot running. Oh, my game fucking worked. Okay. Oh, yes. Okay, now I gotta, yes. Okay. Speed control didn't work, but oops, something got knocked. Oh, my phone! Alright. Hope I didn't break it. Doesn't look like it. Alright. Speed regulation's completely and utterly broke. Yeah, looks like yeah, looks like the encoder readout is busted, but we're so close. So close. I don't know if any of these interrupts are actually firing correctly, to be honest. You know, I did see one -1, some stuff pop up in here, but E50, yeah, because if you look through here, I mean, when it was going backwards, it was showing negative, negative, negative. So the speed control's busted, but pad, read port, encoder A line. Yeah, PC MISC 2. And now that, I mean, it's gotta... One zero zero zero. Did I even set these interrupts correctly? ISC 01, yeah, so 1000 1000 E ICRA EFER. That. Okay, but so, I mean, something was running in here. Well, either way, it, as Danish so kindly pointed out, it is very late. So let's do a little bit of cleanup here. And yeah, so clearly his speed control's working. So the yeah. Yeah, so we've got that, set up encoder. I don't know if these interrupts are doing anything. And, you know, ironic, I don't think we need that. I don't think we need that either anymore. Or that. I think this is just fine. Loop. Controller update, thread sleep milliseconds. Controller update. Yeah, I clearly something is up with the encoder implementation. But other than that, yeah, okay. Other than that, it's pretty close to working, although it's still the encoder. That is what's not working. And that mildly bothers me. All right, so let's see if we can fix it in the next 10 minutes. All right? Okay. And all right, so let's commit what we have. Just so we don't lose anything. And actually, let's set up all of these interrupts at the base here. We'll set up the line modes of things first. Input, output. Change interrupts. All right, yeah. Actually, let's try to bring that back to 4,000 or 400,000. All right, let's put that on the robot. Okay. Yeah. Nice. I did put. Okay, encoder event bits. Encoder state shifted over. Bits. Oh, ooh, that's why. Oh, I forgot to. I wasn't switching on the right variable. If anybody caught that at some point, I would have appreciated you telling me. But all right, all right. Make SCP, and then we're gonna flash this onto the robot. And then we're going to run find cone. Hopefully it won't. All right. Hopefully it won't be too bad. Nope, it's still bad. Okay. I will point the camera at it when it's working. Oops. It's very upset. It's very upset. All right. We'll just rewrite the sketch. That should reset it. All right, disarmed. Waiting for idle. Yeah, okay. It's still not working right. All right, so what you did report during chasing of the... I lost the data. All right, well, we'll do the fine cone. It's going to start spinning up. Let's see. I am counting in the opposite direction that is expecting to count. I see. So the encoder is counting backwards. Okay. We can handle that. We can fix that very, very easily by just switching this to negative and this to add. All right. Make. I can copy that over. Maybe our dude. All right, we're so tantalizingly close. All right. Remote control, and then we'll have it come backwards. Hopefully under. Yes, it is under speed control. Okay, let me point the camera at it. Let me point the camera at it because it's working. Oh my god. Okay. It's midnight. It's past midnight, and we're finally getting the dang thing to work. Okay, droid cam. Okay. So we've got a robot. We're gonna let me cancel that program. We're going to start the find cone program. And it's not happy. Okay. Well, synchronization is definitely a lot more difficult than it used to be because or the Arduino used to reset. There's something about the Arduino sketch, it would reset it every time you open the serial port. Now it doesn't do that anymore, because it's something in the Arduino framework. Either way, so resynchronizing is proving to be now very much of an issue. But so we'll fix that at some point. But so I'm going to start the fine cone process. Okay, and I'm going to switch over to the camera, and the robot should happily drive slowly at a controlled speed and touch the cone and stop. Yes. Okay. Oops, I hit my phone with my chair. All right. And so now I should be able to run the remote control program. And it'll bounce because it switches from forward to backward. And if I hold reverse, it should slowly drive backwards, which you can see that it does. Okay. Alrighty, we freaking did it. Okay, so within the span of one stream, I ported my robot control framework, or I ported the Arduino sketch from I ported it from an Arduino sketch to a ChibiOS project. Okay. So okay, that's a lot. That's a lot. To do detect IMU interrupt, we'll do that in the future. Okay, we're gonna, and it worked with the faster I2C as well. So yeah, we're running an RTOS. So we got threads. We got threads on our chassis controller. We got 2 threads. That's why I was holding my fingers up. We got 2 threads on the chassis controller. And it runs. Hell yeah. Yeah, okay, so we're going to have to do this pin change thing for the IMU data in the future. We got chassis. We got... Okay, yeah, it's running. I mean, it's running. Okay. It only took me 6 hours, so almost a whole work day, but we converted from a sketch to a ChibiOS project. And we have threads. We even did a little bit of refactoring. I need to, I need to merge this, we need to get rid of this encoder logic. What we really need to do is write a abstraction of this encoder. But yeah, I mean, it's counting. We got a packet thread. We've got an update thread. Yeah. Okay. I mean, it's running. I can't complain. It's running. Yeah. So start to finish. So yeah. Let me add. Let me add all this. Git add dot. And sorry, I'm very happy. All right. All right. So git commit chibi rough ChibiOS port chibi. What my git log? Actually, no. We'll just git log. Yeah, git commit -m ChibiOS port early. ChibiOS port is working, although synchronization is now difficult. ChibiOS port is working, although ChibiOS port, let me rephrase this. ChibiOS port works, but synchronization is still rough. All right, push. And we're going to... All right, we're going to say git tag a specific version as v1.1. Or actually, what kind of tags do I have on this repo? 1. Git log tag 1 2024. Tag, or actually, sorry, git checkout, git tag 1.1, git checkout dev, git checkout master, git checkout main. Right, I renamed my branches. Git merge dev, git push, git push, git push. Okay. Okay. And we got it posted publicly anyway. So I've got my contribution. All right, I got my contribution for today already. 12:33 a.m. Okay. So let's see. So recap. It works. Okay. So we ported from an Arduino sketch to a ChibiOS project. We worked through a bunch of some things we didn't realize. We found some broken features in ChibiOS, like the interrupts, or the external interrupts. Clearly, the EXT driver is not the way things are supposed to be anymore. We worked through some race conditions. We worked through implementing an encoder driver, very primitive, encoder controller. But I mean, we went to this channel. We got we converted from a super loop to a threaded system with blocking serial calls. And in terms of how many issues we ran into, in terms of it only took an hour to figure out why the robot wasn't working. Fix up a couple of little bugs. But I mean, we didn't have any major changes. There was that obviously that. So we found that the default samples for ChibiOS use tickless mode, which means you can't use timer 1, which sucks because timer 1 is the best PWM timer on the chip. So we're going to tick mode. Maybe they can do what FreeRTOS does and use the watchdog timers timer, so you can save all your little timers. But either way, it looks like I can't complain. Like that porting process. I mean, it took 6 hours, which isn't the quickest thing in the universe, but it's a hobby project, man. It took 6 hours to move a functional, large, non-trivial Arduino project over to Chibi. So I'm pretty happy about that. So in the future, we'll need to integrate. We'll actually go in and integrate this IMU support. We'll refactor this a little bit to bring the encoder logic out into its own class or something, just so we can try to not have 833 lines of code in one file. But yeah, so we need to get the IMU. We need a little bit of refactoring on some of the drivers. We need to get the IMU, the new IMU working. The whole reason we're moving to ChibiOS is for improved I2C performance. So we need to do that. And then maybe we can even up the serial bit rate now that we can. Now that we have a good model on how to we don't have to spend so much time blocking on. Not to spend so much time blocking on I2C because we spent tons of the C. Every 20 milliseconds we would spend a good millisecond or two just blocked waiting. The IMU would just crush us. But either way, what we and another thing I want to talk about as well is I really want to change the way that my packet system works. Like it's really bad. Like I didn't do a good job on designing the packet protocol system in here. So I want to do a video at some in the near future. I'm working on writing it, but I want to do a video on essentially transmitting data over reliable connections over unreliable transports. And that's going to be on basically how to make a protocol over reliable protocols over UDP. Basically, we're going to implement our own TCP quick type thing over UDP. And I want to get that video up because it's going to have a lot of resources on, or it's going to have a lot of like talking on how to build these reliable, or how to build reliability on top of an unreliable system. Or at least improve reliability in the or a specific definition of reliability on an unreliable transport. And then beyond that, well, we're going to be using UDP in that video, and then which you can guarantee that a packet either arrives or it doesn't, and if it does arrive, it's intact, unless somebody nefarious is forging packets. But that's going to be beyond the scope of things. But assuming no malicious behavior, packets will either not arrive or they will arrive intact. With the serial links, we have to go one layer deeper, which you don't know whether the packet arrived intact. You don't even know what the packet boundaries are if something goes terribly wrong. So that video will also apply to what we're doing with the bare metal 386 project, because we have to get large volume serial data into that in order to reprogram the flash. And so I kind of, there's two videos that are kind of like tugging on each other. So we'll talk about that in the future. But the next time we talk about this robot, we'll be working on the IMU and the current sensor that's in it. So this is going to be my last stream for a couple weeks because I'm going to be away from my computer for a while. So I probably won't be streaming again, or I'll miss the next 2 weeks. So the next stream will be on the 22nd of July. Maybe either the 21st or the 22nd of July. But yeah, thank you so much for watching. I hope you enjoyed it. Again, for anybody who wants to come back and watch me code on things in the future, always feel free to leave a comment. I do try to read the comments. It gives me something to talk about other than making noises as I try to think, right? I really need to put the camera over here so it looks like, because my preview of myself is on my right screen, right? But my camera's over there. Either way. But yeah, hopefully you learned something about ChibiOS. I certainly learned something about ChibiOS because I'd never written any ChibiOS code other than like I compiled the sample. 9 months ago, I compiled the sample. It's like, oh, the sample works. I should look at this in the future. And then I never looked at it. I looked at the docs every once in a while, but never actually wrote my own ChibiOS project. So this was my first time ever writing ChibiOS code, and it was not bad at all. I liked it, and so we'll be looking more into this project, or into, again, we're integrating the new IMU, and we're going to integrate a new current sensor. The current sensor's been in the robot for years, but I never used it. So we'll write a driver for the INA219B, I think is what I put in there. But yeah, then the IMU is the big one, and and eventually we'll rewrite the serial transport system and basically demonstrate all of that and how that would work, and then we'll do a stream about completely gutting the Arduino out of it and designing a Pi Pico 2 based or RP2350 based control board to replace the control board that's in it, because I want to put a mini PC in here at some point, and I need a much bigger power supply. So I need to design a 100-watt USB PD source that my LiPos will drive, and then I'll be able to run a mini PC, and we'll do that design together, hopefully. But yeah, hope you enjoyed watching. And seeing seeing how far we can stretch these poor little Arduino Unos. You know, they're not the fastest things in the world, but you know, they've been largely considered obsolete for a long time now. And to be fair, they are. It's just I got a bunch of them, right? And there's one in there, and it's been doing its job. But you know, I want to switch to more to a substantially improved you know, motor control and stuff in the future, and I need a more powerful processor for some future you know, looking stuff. But we will, before I do that, we will complete, you know, writing a very you know, a stabilized, or you know, reliable system on an Uno, and you know, doing some cool things with the Uno before we replace it. But yeah, thank you for watching. I'm actually still surprised that I actually got this to work in the span of one video. But yeah, thank you all for watching so much. Hope to see you on a future stream.